You are lying down. That much you know. The rest of the world has receded a little, the way it does when the lights are low and there is nothing urgent demanding your attention. There is a surface beneath you. There is air around you. There is a ceiling above you, and perhaps a window nearby. And if there is light coming through that window from somewhere outside, from a street lamp or a moon or a distant house, that light is falling across the ceiling at a particular angle. You did not choose that angle. You did not measure it. But it is there, as real as anything else in the room, and it is following a rule. Everything with an angle, everything that slants or tilts or bends, is quietly obeying a set of relationships that people worked out over a very long time. Not all at once, not in one place. Piece by piece, across centuries and across continents, by people who never met each other and who spoke different languages and who had different reasons for caring about the shape of a shadow or the slope of a roof or the path of a star across the night sky. Those relationships are still here. They are still working. They are still holding up the ceiling above you and guiding the light across it and keeping your spine in the exact position it has chosen to rest in tonight. Tonight, we are going to walk through all of it. Not the way you might remember from a classroom, with equations to memorize and tests to pass. There is no test. There is nothing to hold on to tightly. There is just a long, slow walk through an old and useful idea, and you are welcome to drift in and out of it as much as you like. If you fall asleep somewhere along the way, that is fine. That is the point. The ideas will still be here tomorrow night if you want to come back to them. They have been here for thousands of years already. They can wait a little longer. We will start where it all started, which is not in a classroom and not in a textbook, but in a place with a great deal of flat land and a very bright sun and a river that flooded every year without fail. That place was ancient Egypt, along the Nile, somewhere around 4,000 years ago. And the problem that started everything was not abstract. It was not philosophical. It was about property lines. Every year, the river would rise. It would spread out over the fields on either side, covering the land with water and silt, and then it would recede again, leaving behind a fresh layer of dark, rich soil that was perfect for farming. This was good for growing things. It was terrible for boundaries, because the flooding would wash away any markers people had placed to show where one person's land ended and another person's land began. Stakes would be knocked over. Stones would be buried in mud. The flood did not care whose field was whose, so every year after the water went down, someone had to go back out into the fields and remark the boundaries. This was not optional. If you did not know where your land was, you could not plant it, and if you could not agree with your neighbor about where the line ran between your fields, there would be disputes that no one wanted to settle. The people who did this remarking were called rope stretchers. That is a literal translation of what they were called in the old texts. They used long ropes with knots tied into them at regular intervals, and they would walk out into the muddy fields and stretch those ropes across the ground to measure out distances and to construct corners. They needed to make right angles, perfect square corners, because the fields were usually rectangles, and the boundaries had to meet at right angles or the whole system of measuring would fall apart. A field with a crooked corner would throw off the measurement of everything else. So they needed a reliable way to make a perfectly square corner every single time, regardless of how much mud there was, or how tired they were, or how bright the sun was beating down on them. And they had one. It was simple, it was reliable, it worked every time. They took a rope with 12 equally spaced knots. They formed it into a triangle, with sides of 3-knot intervals, 4-knot intervals, and 5-knot intervals. And when they pulled that triangle tight, the angle across from the longest side, the side with 5-knot intervals, was always a perfect right angle. Always. Every single time. Regardless of how big the triangle was, so long as the proportions remained the same. They did not know why this worked. Not in a way they could prove. But they did not need to know why. They only needed to know that it did work, and they used it constantly, for fields and for temples and for pyramids, for anything that required a square corner and a straight line. This is worth sitting with for a moment. The rope stretchers had found one specific relationship between the sides of a triangle and its angles. They had not yet generalized it. They had not yet realized that this relationship was part of a larger pattern that applied to every triangle, to every angle, to every slope and every slant in the world. But they had the seed of it. They had the first piece. They had a right angle that they could make reliably, without instruments, without calculations, using nothing but a rope with knots tied into it. That is the first step. That is where trigonometry begins. Move now to Babylon, in Mesopotamia, a bit later in time, though there is overlap. The Babylonians were extraordinary record keepers. They wrote in wedge-shaped marks pressed into wet clay, and thousands of their clay tablets have survived, buried in the dry earth for thousands of years. One of these tablets is now called Plimpton 322, and it contains something remarkable. It is a list of numbers, columns and columns of numbers, arranged in a way that suggests they were not random. They were not measurements of anything physical. They were, in effect, a systematic exploration of which sets of 3 numbers could form the sides of a right triangle. They were finding more triples like the 3, 4, 5 triple the Egyptians had used with their knotted ropes. They were finding them in a more organized way, and they were working with numbers far larger than the simple 3, 4, 5 combination. The Babylonians were doing something the Egyptians were not doing. They were exploring the pattern itself. They were not just using the first example they had found. They were looking for all the examples. They were collecting them. They were arranging them in tables. This is the kind of pattern hunting that eventually leads to a general rule, a principle that covers every case rather than just a few special ones. The Babylonians never developed a full general theory. They never had our modern notation. They never used the words sine or cosine. But they were moving in that direction. They were building a foundation that others would later build upon. There is another thing the Babylonians gave us that you carry with you every single day without thinking about it. They divided the circle into 360 parts. 360 degrees. Nobody is entirely sure why they chose that number, though there are good guesses. Their number system was based on 60, not on 10. This might seem strange to us because we count in tens, but 60 is a wonderfully practical number for dividing things. It can be split evenly into halves and thirds and quarters and fifths and sixths and tenths and 12th parts. Many divisions come out cleanly without leftovers. 360 is 6 times 60, and it is also close to the number of days in a year, which the Babylonians tracked carefully for their calendars. Whatever the exact reason, the choice stuck. 360 degrees in a circle is still what we use today. Thousands of years later, every time anyone talks about turning around or facing a new direction or measuring the slope of a roof. So already, before trigonometry existed as a subject, 2 ancient civilizations had planted 2 separate seeds. The Egyptians had discovered that specific triangles held reliable relationships between sides and angles. The Babylonians had begun systematically searching for those relationships and had given the world its enduring way of measuring angles. But neither civilization had pulled these threads together into a single unified framework. That step needed something else. It needed the sky. Because here is the problem that drove trigonometry forward for the next many centuries. The problem of predicting where things would be in the sky. When would the flood come? When should crops be planted? When would an eclipse happen? Where would a particular star be on a particular night? These were not idle questions. They mattered enormously for agriculture and for religious ceremonies timed to the seasons, and for navigation, especially for sailors who had no other way to know their position once they lost sight of land. To answer these questions, ancient astronomers needed a way to describe positions in the sky and to calculate how those positions changed over time. The sky, it turns out, is essentially a set of circles. The sun appears to trace a circular path against the background stars over the course of a year. The moon traces its own path. The stars appear to rotate around fixed points as the earth turns beneath them. To describe circular motion precisely, you need a way to talk about angles. You also need a way to relate those angles to straight-line distances. If a star is a certain angular distance above the horizon, how high is that in a measurable way? If two stars are separated by a certain angle in the sky, how far apart do they appear? This is the gap between simple angle counting, which the Babylonians had, and a full working system for calculating with angles. And the person who first built a bridge across that gap was a Greek astronomer named Hipparchus, who lived about 1800 years before now. He worked mainly on the island of Rhodes, and he is often called the father of trigonometry. The title is fair. What Hipparchus did was construct what is called a table of chords. A chord, in the language of circles, is a straight line connecting 2 points on the edge of a circle. If you know the angle at the center of the circle between those 2 points, you can calculate the length of that chord as a fraction of the circle's radius. Hipparchus built an enormous table cataloging the chord lengths for many different angles. He would have worked by hand, doing careful geometry and arithmetic over and over for each angle. There were no calculators, there was only reasoning and patience. This table of chords was a powerful tool. An astronomer could look up the chord length associated with a given angle and use that information to track the motion of the sun or the moon or a planet. For the first time, angles in the sky could be converted into measurable distances. It was not yet trigonometry as we know it, but it was the direct ancestor. The next great leap came a few centuries later from an astronomer working in Alexandria in Egypt, named Claudius Ptolemy. Ptolemy wrote an enormous astronomical text that would become known as the Almagest, an Arabic word meaning roughly the greatest. Inside that text, he expanded on Hipparchus's work. He refined the table of chords and extended it, and he used it as the mathematical backbone for an entire model of the universe, one where the Earth sat at the center, and the sun and moon and planets moved around it on complicated circles within circles. We know today that Ptolemy's model was wrong. The Earth is not the center. But here is something worth sitting with. Ptolemy's trigonometric methods were sound. They worked. They let him predict where planets would appear in the sky on future dates with real accuracy, even though his underlying picture of why they moved that way was incorrect. The mathematics was separable from the astronomy it was built to serve. It would go on to outlive the wrong model entirely, surviving the correction that came centuries later when the sun was placed at the center instead. So by this point, we have chords. We have a circle divided into 360 degrees. We have serious mathematical machinery built for tracking the sky. But we do not yet have sine or cosine or anything that would look familiar from a classroom. That transformation happened next, and it happened somewhere else entirely. The scene shifts now, east and south, to India. Indian mathematicians and astronomers, working within their own long tradition, took the idea of the chord and made a small change to it. Instead of measuring the full chord, the whole straight line across the circle, they began measuring half of it instead, half the chord. This small change is the single most important shift in the history of the subject, because that half chord is essentially exactly what we now call the sine of an angle. An astronomer and mathematician named Aryabhata, working in India around 1500 years before now, used a term for half-chord in his writings. That term was in Sanskrit. Over time, it was shortened and passed along through trade and scholarship into the Arabic-speaking world. It moved then into Latin through a chain of translations, and in that process, something almost accidental happened. The Sanskrit term was translated phonetically into Arabic, and the resulting word happened to sound like an existing Arabic word for a curve or a bowstring. Centuries later, when European scholars translated the Arabic texts into Latin, they chose a Latin word for a bay or a curve or a fold. That Latin word was sinus, and sinus, over time, became sine, the word you know today. It is worth pausing on this quietly. The word sine may feel abstract, like a mathematical label with no history, but it carries inside it a chain of translations, stretching from Sanskrit astronomy through Arabic scholarship into Latin, and each step of that chain slightly bent the meaning, the way a phrase shifts each time it is passed from one language to another. And yet the word still points at the exact same mathematical idea the whole way through. Half a chord, a straight line drawn across part of a circle. That idea survives, unchanged, underneath the layers of language. That half-chord idea connected directly and cleanly to right triangles in a way that full chords did not. If you have a right triangle, a triangle with one 90-degree corner, the sine of one of the other angles is the ratio between the side opposite that angle and the longest side of the triangle. The longest side is called the hypotenuse. Let us slow down here and work through that image a few different ways. Picture a ladder leaning against a wall. The ladder itself is the hypotenuse. It is the longest side of the triangle formed by the ladder and the wall and the ground. The angle the ladder makes with the ground is one of the two non-right angles. The height the ladder reaches up the wall is the side opposite that ground angle. The sine of that angle is simply the height reached divided by the length of the ladder itself. If the ladder is steep, nearly vertical, the angle at the ground is large and the height reached is close to the ladder's full length. The sine is close to 1. If the ladder is laid almost flat along the ground, the angle is small and the height reached is tiny compared to the ladder's length. The sine is close to 0. That is the whole idea. Sine measures, as a simple ratio, how much of a slanted length gets converted into height for a given angle. Every angle between 0 and 90 degrees has its own fixed sine value. A short ladder and a long ladder leaned at the exact same angle will have the exact same ratio between height and length. That is what makes sine useful. It strips away the specific size and gives you something universal about the angle alone. There is a companion idea sitting alongside sine, and it is called cosine. Once you understand sine, cosine is almost free. It is simply the sine of the complementary angle, the angle left over once you subtract your angle from 90 degrees. In the ladder picture, while sine tells you how much height the ladder reaches, cosine tells you how far the base of the ladder sits away from the wall, again as a ratio to the ladder's length. When the ladder is steep, the base sits close to the wall. Cosine is close to 0. When the ladder lies nearly flat, the base sits far from the wall. Cosine is close to 1. Sine and cosine trade off against each other. As one grows, the other shrinks. This trade-off is not arbitrary. It comes directly from the geometry of the right triangle, from the fact that the two non-right angles in any right triangle always add up to 90 degrees. As one angle grows, the other shrinks, and their ratios shift in a locked, predictable way. Let us say all of that once more in a slightly different way. Imagine standing at the base of a triangle, looking up along its hypotenuse toward the far corner. Sine of your viewing angle tells you what fraction of that slanted length is height, straight up. Cosine of that same angle tells you what fraction of that slanted length is spread out horizontally along the ground. Every slanted line, no matter how long, can be broken down into these two components, an upward part and a sideways part. Sine and cosine are exactly the tools that do that breaking down, expressed as clean ratios that depend only on the angle, never on the length of the line itself. That single idea, breaking a slanted length into an upward part and a sideways part, is the seed for nearly everything that comes next. Measuring the height of a mountain, charting a course across an ocean, designing a roof that will bear its own weight. All of it comes back to this one repeated act, taking something slanted and splitting it into how much goes up and how much goes sideways. And that is where we will pause for now, with that image of the ladder and its two shadows, one falling up the wall and one falling along the ground. The rest of the story is still ahead, but this is the center of it. This is the idea that everything else grows from: a slanted line, a right angle, and two simple ratios that never change for a given slant. Now let your eyes rest where they are. Let your breath slow if it has not already. The room is still around you, holding you the way it has been the whole time. And somewhere in the quiet dark, that angle between the ladder and the ground, between the slant and the flat, is still quietly holding steady, the way it has been holding steady for thousands of years, the way it will keep holding steady long after this room has gone still and the light outside has shifted and changed and come back again. The rope stretchers had found something that worked. They did not know why it worked, not in the way we might mean when we say we understand something. They knew that if you took a rope with 12 evenly spaced knots and arranged it into a triangle with sides of 3 knots, 4 knots, and 5 knots, the angle across from the longest side would always be square. Perfectly square, a right angle. They used this knowledge every year. When the floodwaters receded and the fields had to be measured out again, they pulled their ropes tight in the mud, made their triangles, laid out their corners, and went back to their homes. They did not ask why the 3, 4, 5 triangle produced a right angle. They did not need to. It was enough that it worked. But there is a quiet question buried in that fact, and it is the kind of question that eventually grows into something much larger. The rope stretchers were using a relationship between the sides of a triangle, 3, 4, and 5. They were not thinking about angles as separate from sides. They were thinking about lengths. But the right angle was there, reliably, every time, because the sides happened to be in that particular ratio. Change the ratio, and the angle changes with it. A triangle with sides of 2, 3, and 4 has a different angle across from its longest side. It is not a right angle, it is something else, wider or narrower, depending on how the sides are arranged. The relationship between the sides and the angles is not arbitrary. It is fixed. It is rule-governed. The rope stretchers had found one example of that rule, but they had not yet seen the rule itself. Move now from Egypt to Babylon, a region in what is now Iraq, where another civilization was working on the same set of questions from a different direction. The Babylonians were not rope stretchers in the same way. They were record keepers. They wrote on clay tablets, pressing wedge-shaped marks into the soft clay with a stylus, then baking the tablets hard in the sun or in a kiln. Thousands of these tablets have survived, buried in the earth for thousands of years, and many of them are mathematical. They contain tables of numbers, calculations, problems, and solutions, all written in that wedge-shaped script we now call cuneiform. One of these tablets, now known as Plimpton 322, is among the most important pieces of ancient mathematics that has come down to us. It is a small clay tablet, broken along one edge, but the numbers on it are clear enough to read. They are arranged in columns. The columns contain what appear to be lists of numbers, and the numbers, when you examine them carefully, turn out to be sets of 3 numbers that form the sides of right triangles. Not just the simple 3, 4, 5 combination the Egyptians used, but many others, far larger, far more complex. The Babylonians had been exploring these triples systematically, finding every combination they could, and recording them in tables. This is a shift in approach that matters. The Egyptians had found one example and used it. The Babylonians had found many examples and were studying them. They were looking for the pattern underneath the individual cases. They were hunting for the rule that generated all the triples, not just one convenient one. It is not clear how far they got in understanding that rule, because their notation was different from ours, and we do not have all of their work. But the tablet itself is evidence of a mathematical mind at work, one that was not satisfied with a single reliable trick, but wanted to see the full shape of the territory. There is another Babylonian contribution that you carry with you every day, and it is so familiar that you almost certainly never think about it. The Babylonians divided the circle into 360 parts, 360 degrees. This choice was not inevitable. Other cultures divided circles differently, but the Babylonian system was practical and easy to work with, and it spread through the ancient world, passed along by traders and astronomers and scholars, until it became the standard way of measuring angles everywhere. Why 360? There are several plausible explanations. The Babylonian number system was based on 60, not on 10, which meant they were comfortable working with numbers that divided evenly in many ways. 60 is divisible by 2, 3, 4, 5, 6, 10, 12, 15, 20, and 30. It is a flexible number for calculations. 360 is 6 times 60, and it is also roughly the number of days in a year, which mattered to the Babylonians for their calendars. Whatever the exact reasoning, the choice stuck. It was transmitted through Greek astronomy, through Islamic scholarship, into medieval Europe, and from there into the modern world. Every time you hear someone talk about a 90-degree angle or a full 360-degree turn, you are using a Babylonian unit chosen thousands of years ago on the banks of the Tigris and Euphrates. So by this point, before trigonometry existed as a named subject, two ancient civilizations had planted two separate seeds. The Egyptians had the practical knowledge that certain triangles had reliable relationships between sides and angles. The Babylonians had begun the systematic study of those relationships, and they had given the world a consistent way to measure angles. But neither civilization had connected these two threads into a general theory. The idea that every angle has a fixed set of ratios associated with it, ratios that can be calculated and tabulated and used to predict distances and heights, had not yet been articulated. That step needed a new kind of problem. It needed a problem that forced people to think about angles and distances together, not as separate things, but as two aspects of the same geometric reality. And that problem came from the sky. Ancient peoples across many cultures looked up at the night sky and saw patterns. They saw stars that rose and set at predictable times, stars that moved in regular paths across the seasons, and a moon that changed its shape in a cycle that repeated with reliable precision. They did not know what these objects were, not in the way we might mean today, but they knew when they would appear and where they would be. That knowledge mattered. It was tied to agriculture, to religious ceremonies, to navigation, to the rhythm of daily life. If you knew when the flood would come, you could plant your crops at the right time. If you knew when a particular star would rise, you could time a festival. If you could follow the path of the sun across the sky, you could orient a temple or a tomb. But knowing when and where is not the same as knowing how. The sun moves across the sky in a circular arc. The stars rotate around a fixed point. The moon travels through its phases in a repeating cycle. These motions are circular, and circular motion requires a way to talk about angles and positions. A star that is 30 degrees above the horizon is in a different place than a star that is 60 degrees above the horizon. But what does that difference mean in terms of actual distance, measurable distance, the kind of distance you could use to calculate the height of a building or the width of a river? This is where the gap was. The Babylonians could measure angles. They had their 360 degrees, but they did not have a way to convert those angles into distances. They could not look at a star and say, with any precision, how high it actually was in a measurable sense. They could say it was 40 degrees above the horizon, but that was an angular measure, not a linear one. The missing piece was a systematic way to translate angles into ratios, ratios that could be applied to any triangle, any circle, any situation where an angle needed to be tied to a length. The person who first built a bridge across that gap was a Greek astronomer named Hipparchus. He lived around 1800 years before now, on the island of Rhodes, which was a center of learning and trade in the ancient Mediterranean. Hipparchus is often called the father of trigonometry, and the title is earned because he did something that no one had done before. He constructed a table of chords. A chord, in the language of circles, is a straight line connecting 2 points on the circumference of a circle. It is not the curved part of the circle itself. It is the straight cut across the inside, the line that joins 2 points on the edge. If you have a circle and you know the angle at the center between the 2 points, you can calculate the length of that chord, but only if you have a systematic way to do the calculation. Hipparchus built a table that gave the chord length for many different central angles, in increments across the circle. The table was essentially a reference work. You looked up the angle, and the table told you the corresponding chord length, relative to the radius of the circle. This may sound like a dry technical achievement, but it was a powerful tool. It meant that an astronomer could take an angular measurement from the sky and convert it into a straight line distance that could be used in calculations. The path of a star, the position of the moon, the timing of a predicted eclipse. All of these could be approached using the same basic method. Measure the angle, look up the chord, use the chord to calculate something else. Hipparchus's table was not trigonometry in its modern form. There was no sine, no cosine, no tangent. But it was the direct ancestor. It was the first time anyone had created a systematic mapping from angles to lengths, and that mapping is the heart of everything that follows. The work of Hipparchus was later extended by Claudius Ptolemy, an astronomer working in Alexandria, Egypt, about 3 centuries later. Ptolemy is best known for his astronomical model, which placed the Earth at the center of the universe and had the sun, moon, and planets moving around it in a complex system of circles within circles. That model was wrong, as we know today. The Earth is not at the center. But Ptolemy's mathematics was not wrong. He used the table of chords to calculate the positions of the planets with a degree of accuracy that was useful for practical purposes. His predictions of planetary positions were good enough to be used by astronomers and astrologers for centuries after his death. There is a lesson in Ptolemy's work that is worth holding on to. A mathematical tool can be useful even if the framework it is embedded in is later shown to be incorrect. Ptolemy's chord calculations were sound. They produced correct answers for the positions of planets, even though his explanation of why those positions occurred was based on a false premise. This happens more often than you might think. Mathematics and physical interpretation are not the same thing. Mathematics provides the relationships. The interpretation tells you what those relationships mean in the world. Ptolemy had the relationships right, even if he had the meaning wrong. The table of chords served its purpose for centuries, but it had a limitation that later mathematicians would address. The chord is a full straight line across the circle. It does not tie as neatly to right triangles as the half-chord does, and it was the half-chord, developed later in a different part of the world, that would ultimately give us sine and cosine. The story now moves east, to India, in the centuries after Ptolemy. Indian mathematicians and astronomers had their own long tradition of sky watching and calculation. They inherited some of the Greek work, but they also developed their own approaches, and in some cases, they made improvements that would eventually reshape the entire subject. The improvement that matters most for our story is the shift from the full chord to the half chord. If you take a circle and draw a chord between 2 points, and then drop a perpendicular line from one of those points down to the radius of the circle, the half chord is the length of that perpendicular segment. It is the distance from the point on the circle to the radius line, measured at a right angle. This is a cleaner quantity to work with when you are dealing with right triangles, because it fits naturally into the geometry of the triangle formed by the radius, the half chord, and the segment along the radius. The Indian mathematician Aryabhata, who lived around 1500 years before now, used this half-chord idea in his astronomical works. He gave it a name in Sanskrit, a term that translated roughly to half-chord or half-string. That term, and the idea behind it, would travel west over the following centuries, passing through the Islamic world and eventually into Europe, and along the way, the name would change in ways that were partly accidental and partly a result of translation. This is where the word sine comes from, and the chain is worth following because it shows how ideas travel across cultures. The Sanskrit term was translated into Arabic, and the translators chose a word that sounded similar but also had a meaning in Arabic that was close to the geometric idea. The Arabic word they used could mean curve or bowstring, which fit with the half-chord image. Later, when Arabic mathematical texts were translated into Latin, the translators chose a Latin word that captured the same sense. They used sinus, which in Latin could mean a bay, a fold, or a curve. And that Latin word, over time, became sine, the term we still use today. It is a quiet thing to hold on to, the way a word can travel across languages and centuries, picking up different associations along the way, and still end up pointing at the same geometric object. The sine is the half-chord. It is the distance from the edge of the circle to the radius line, measured at a right angle. That idea did not change as it moved from Sanskrit to Arabic to Latin to English. Only the word changed, shifting slightly with each translation until the original name was almost entirely lost. But the idea remained, carried along by the people who needed it for their calculations, passed from hand to hand and from text to text, until it became part of the mathematical furniture of the world. This half-chord idea is the foundation of modern trigonometry. It gives us sine directly. And from sine, cosine follows naturally, because cosine is simply the sine of the complementary angle, the angle that completes the right triangle. Where sine tells you the ratio of the opposite side to the hypotenuse, cosine tells you the ratio of the adjacent side to the hypotenuse. They are two sides of the same coin, two measures of the same right triangle, taken from different angles. If you picture a right triangle, with one angle at the base and the right angle at the corner opposite the hypotenuse, sine of that base angle is the height of the triangle divided by the length of the slanted side, the hypotenuse. Cosine is the length of the base, the horizontal side, divided by the same hypotenuse. Both are ratios, both depend only on the angle, not on the size of the triangle. A tall, thin triangle and a short, wide triangle, if they have the same base angle, will have the same sine and cosine values, because those values are determined by the angle itself, not by the dimensions of the triangle. This is the principle that makes trigonometry useful. It abstracts away from the specific situation and gives you a general relationship that applies everywhere. Once you know the sine of a given angle, you can apply it to any triangle that has that angle, regardless of its size. You can use it to calculate a height from a distance, or a distance from a height, or any other pair of measurements that involve a right triangle and a known angle. The rope stretchers were doing this implicitly, without the language to describe it. They knew that 3, 4, 5 gave a right angle, but they did not know that the sine of that right angle was 1, or that the cosine was 0, because those concepts had not yet been invented. The half-chord idea, and the sine that grew from it, changed that. It gave people a way to talk about angles and sides together, not as separate things but as two aspects of the same relationship. It turned trigonometry from a set of practical tricks into a coherent subject, with its own structure and its own patterns. And that structure would continue to grow over the centuries that followed, as the sine traveled west through the Islamic world, where scholars would extend it and refine it, and then into Europe, where it would be further developed into the form we recognize today. But that is the next part of the story. For now, the half-chord, the sine, is the central idea. It is the answer to the question the rope stretchers did not ask. Why do the sides and angles of a triangle relate to each other in the way they do? The answer is that they are tied together by ratios. Ratios that are fixed for each angle, and those ratios can be calculated and tabulated and used for any purpose where angles and distances meet. That is the insight, and it is the seed from which everything else grows. The half-chord was a small change, but it was the kind of small change that opens a door to a larger room. The full chord told you the straight line distance across the circle between 2 points. The half-chord told you the distance from one of those points to the radius line, measured at a right angle. It was a more natural quantity to work with when you were dealing with right triangles, because the half-chord fit directly into the geometry of a right triangle formed by the radius, the half-chord, and the segment along the radius. Think of it this way. A circle has a center and a radius. The radius is a straight line from the center to the edge. If you take a point on the edge of the circle and draw a line from that point straight down to the radius line, meeting it at a right angle, the length of that vertical line is the half-chord. It is the distance from the edge of the circle to the radius line, measured perpendicular to the radius. That length changes as the point moves around the circle. When the point is at the top of the circle, the half-chord is equal to the radius. When the point is at the side of the circle, the half-chord is 0. And for every position in between, the half-chord takes a value between 0 and the radius, depending on the angle. This is the sine. The half-chord, measured relative to the radius, is the sine of the angle at the center. If the radius is 1 unit, the sine is simply the half-chord itself. If the radius is larger, the sine is the half-chord divided by the radius, a ratio that depends only on the angle. That ratio is what makes sine useful. It strips away the size of the circle and gives you a number that belongs to the angle alone. The Indian mathematicians who developed this idea did not call it sine. They had their own term, their own way of thinking about it. But they understood the relationship. They knew that the half-chord varied with the angle in a regular, predictable way, and they used that knowledge in their astronomical calculations. They were tracking the positions of the sun and the moon and the planets, just as the Greeks had done, but they had a slightly different tool for the job. The half-chord was more flexible than the full chord. It was easier to work with. It fit more naturally into the mathematics of right triangles. Over the following centuries, this Indian mathematics traveled west. It moved through trade routes and through the movement of scholars, passing from India into the Islamic world, where it was received with interest and extended further. The Islamic scholars of this period were among the most advanced mathematicians in the world. They had access to Greek texts, Indian texts, and their own developing traditions, and they synthesized these influences into a rich and productive mathematical culture. They translated works from Greek and Sanskrit into Arabic, and they added their own contributions to what they received. One of the scholars who worked with these ideas was al-Battani, an astronomer and mathematician who lived around 1100 years before now. Al-Battani refined the sine and introduced a related concept that we now call tangent. Tangent is the ratio of the opposite side to the adjacent side in a right triangle, or equivalently, the ratio of sine to cosine. It tells you the slope of a line, how steeply it rises relative to its horizontal run. Al-Battani used tangent in his astronomical work, improving the accuracy of his calculations for the positions of the sun and the moon. Another scholar from this period, al-Khwarizmi, is perhaps even more familiar by name, because his name passed into Latin as algorithm, and that word now describes the step-by-step procedures that computers follow. Al-Khwarizmi worked broadly across mathematics, including algebra and arithmetic, but his work on systematic calculation methods was part of the larger effort to make mathematics practical and reliable. The trigonometric tables that scholars used for their calculations required careful, consistent methods to generate and verify. Al-Khwarizmi and his contemporaries built those methods, ensuring that the tables were accurate enough to be trusted. There is a quieter figure from this tradition worth mentioning, a scholar named Nasir al-Din al-Tusi, who lived in Persia around 750 years before now. Al-Tusi wrote a treatise on trigonometry that is often considered the first work to treat the subject as an independent branch of mathematics, separate from astronomy. Before Al-Tusi, trigonometry was largely a tool for solving astronomical problems. It was a technique, not a subject in its own right. Al-Tusi argued that trigonometry had its own internal structure, its own theorems and relationships, and that it could be studied for its own sake, not just as an aid to skywatching. This was an important shift. It meant that trigonometry could develop in directions that were not tied to astronomy, that it could be extended and refined by people who were interested in the mathematics itself, not just in its applications. The word sine, as we use it today, entered the European languages through the same translation pathway that carried the Indian half-chord into the Islamic world and then into Europe. The Sanskrit term was translated into Arabic, and the Arabic term was translated into Latin. The Latin word was sinus, which could mean a bay, a fold, or a curve. That word over time became sine. The word carries with it the history of its travels, though you would not know it by looking at it. It seems like a simple mathematical label, but it has a longer story behind it. The European mathematicians who received this inheritance were largely working in Spain and Italy, where contact with the Islamic world was strongest. Cities like Toledo in Spain became centers of translation, where scholars worked to render Arabic texts into Latin. These translations made the mathematical works of the Islamic world accessible to European scholars, who had largely lost touch with the Greek mathematical tradition. The translation movement was slow and painstaking, but it brought a wealth of knowledge into Europe, including trigonometry. A German mathematician named Regiomontanus, working around 550 years before now, was one of the figures who helped organize this knowledge into a systematic form. He wrote a treatise on trigonometry that presented the subject clearly and coherently, with applications to astronomy, but also to surveying and navigation. Regiomontanus was aware that trigonometry could be used for more than just predicting the positions of stars. It could be used to measure the height of a building, the width of a river, the distance to a distant mountain. These were practical problems that mattered to surveyors and engineers, not just to astronomers. The applications to navigation were particularly important. European ships were beginning to sail farther from home, out into the open ocean, where there were no landmarks to guide them. A sailor could navigate along a coast by following its shape, but once the coast was out of sight, there was nothing to see except the sky and the water. The sky could provide guidance, if you knew how to read it. The position of the sun at noon, the height of a familiar star above the horizon, the angle between the horizon and a celestial body. These measurements could tell you where you were, but only if you could translate them into distances. Trigonometry provided the translation. It was the tool that turned a star's angular height into a ship's latitude. The mathematics of navigation is essentially the same as the mathematics of surveying. Both involve measuring angles and using those angles to calculate distances. A surveyor on land might measure the angle to a distant mountain peak from two different positions and use those two angles to calculate the mountain's height. A sailor at sea might measure the angle of the sun above the horizon at noon and use that angle to calculate how far north or south they were. The underlying logic is the same. Measure an angle, apply a trigonometric relationship, and get a distance. This is the power of the sine and cosine. They are tools that let you move between angles and lengths, between the angular world of the sky and the linear world of the earth. They bridge the gap between what you can see and what you can measure. The rope stretchers on the Nile were doing this implicitly, without the language or the tables. They knew that 3, 4, 5 gave a right angle, but they did not have a way to generalize that knowledge to other angles. The sine and cosine gave that generalization. They provided a way to handle any angle, not just the ones that came from simple ratios. At this point in the story, trigonometry was still tied to specific circles and specific triangles. The sine and cosine were defined in terms of a particular circle with a particular radius. If you changed the radius, the values changed. This was fine for practical work, but it limited the ways you could think about the subject. The relationships between angles and sides were not yet abstract. They were still tied to the physical diagram you had drawn. The next development, which would happen in Europe over the following centuries, was the shift from geometry to function. Mathematicians began to treat sine and cosine as abstract rules, independent of any particular circle or triangle. An angle was an input, and the sine was an output. The output did not depend on the size of the circle or the length of the sides. It depended only on the angle. This was a subtle shift, but it changed everything. It made trigonometry a branch of pure mathematics, not a collection of practical techniques. It opened the door to new applications, because the sine and cosine were no longer tied to any particular physical situation. They could be applied wherever angles and ratios occurred, whether that was in a triangle on a page, the path of a planet, or the shape of a wave. The French mathematician François Viet, working around 450 years before now, was one of the first to think about sine and cosine in this abstract way. He wrote them as formulas, not as geometric constructions. He showed that the relationships between angles and sides could be expressed algebraically, using symbols and equations, not just drawn on a page. This was a significant shift in the way mathematics was done. It moved trigonometry from a visual subject to a symbolic one, and that symbolic form would be essential for the applications that came later. The person who completed this transformation was Leonhard Euler, a Swiss mathematician who lived in the 18th century, around 280 years before now. Euler is one of the most important figures in the history of mathematics. He worked across almost every branch of the subject, and he made contributions that are still central to how we think about mathematics today. In trigonometry, his most important contribution was to define sine and cosine in terms of the unit circle, a circle with a radius of exactly 1. This was a simple change, but it was transformative. By fixing the radius at 1, Euler removed the last trace of dependence on physical size. The sine and cosine became pure functions of the angle alone. They were no longer tied to any particular circle or triangle. They were simply the vertical and horizontal coordinates of a point moving around a circle of radius 1. This definition is the one we still use today, and it is the definition that makes sine and cosine so useful. It frees them from the constraints of geometry and lets them be applied to any situation where circular motion or wave behavior occurs. Euler also introduced a new way of measuring angles. The Babylonian system of degrees had served well for thousands of years, but it was arbitrary. The choice of 360 degrees was based on historical accident, not on any fundamental property of geometry. Euler proposed a different unit, called the radian, which measures an angle by the length of the arc it traces out on the unit circle. A full circle has an arc length of 2 times pi, where pi is the ratio of a circle's circumference to its diameter, so a full circle is 2 pi radians. A half circle is pi radians. A quarter circle is pi over 2 radians. This may sound more complicated than degrees, but it has a fundamental simplicity. It connects angle measurement directly to the geometry of the circle itself, not to an arbitrary historical choice. The radian is the natural unit for trigonometry because it makes the relationships between angles and arc lengths simple. If you use radians, the sine and cosine of an angle have clean derivative relationships, which is important for calculus. The derivative of sine with respect to angle is cosine, and the derivative of cosine is negative sine. These relationships are simple and elegant when angles are measured in radians. They are cluttered with factors of pi over 180 when angles are measured in degrees. Radians are the language of advanced trigonometry, the language that lets you connect trigonometry to the rest of mathematics. By this point, the modern framework was in place. Sine and cosine as functions of an angle, defined by the unit circle, measured in radians. Tangent and the other trigonometric functions defined in terms of sine and cosine. A set of relationships that connect these functions to each other and to the geometry of right triangles. This framework is what you would recognize from a mathematics classroom if you have ever seen trigonometry presented that way. But it took thousands of years to reach this point, and the journey involved many cultures and many different approaches to the same underlying questions. The trigonometric functions are not just abstract symbols. They are descriptions of something real. The sine of an angle is the ratio of the opposite side to the hypotenuse in a right triangle. It is also the vertical coordinate of a point on the unit circle. It is also the height of a wave at a given point in its cycle. All of these descriptions are the same function, expressed in different contexts. The sine is one thing, appearing in many places. This is the quiet core of trigonometry, a single set of relationships, discovered piece by piece over thousands of years, by people who did not know they were working on the same problem. The rope stretchers on the Nile were measuring fields with knotted ropes. The Babylonian scribes were recording tables of right triangle triples on clay tablets. The Greek astronomers were building tables of chords to track the stars. The Indian mathematicians were working with half-chords. The Islamic scholars were refining and extending these ideas. The European mathematicians were abstracting them into functions, and Euler was giving them their final form in terms of the unit circle and the radian. All of this work, across all of these cultures, was pointing at the same set of relationships, a point moving around a circle, 2 coordinates, sine and cosine, the relationships between them, the way they change as the angle changes, the way they connect angles to distances, the way they appear in the sky and on the earth, and in the sound of a voice. The same mathematics, discovered and rediscovered, refined and extended, until it became the framework we use today. And all of that is still here, in the room with you. The sine and cosine are not just ideas from a textbook. They are the mathematics that describes the angle of the light falling across the ceiling, the angle of your elbow, the angle between your spine and the mattress. They are the mathematics that describes the sound in your ears, if there is sound. They are the mathematics that describes the motion of the satellites above you, the ones that tell your phone where you are. They are the mathematics that describes the orbit of the Earth around the Sun, the motion that carries you through space even as you lie still. It is a quiet thing to be lying in a room, surrounded by mathematics that you do not have to think about. The sine and cosine are working in the background, in the structure of the room, in the sound of the air, in the light on the ceiling. They have been working for thousands of years, and they will keep working after you have fallen asleep. They do not need you to understand them, but if you want to, you can. That is what tonight is for. A slow walk through an old idea, with no destination and no test, just the sense of being carried along by something that has been here the whole time. The shift from the full chord to the half chord was a quiet turning point, the kind that only becomes visible in hindsight. The Indian mathematicians who made that shift were not trying to invent a new branch of mathematics. They were trying to solve the same problems that had occupied astronomers for centuries, tracking the motions of the sun and the moon and the planets across the sky. But their choice to work with half the chord rather than the whole chord turned out to be the key that unlocked a simpler, cleaner way of thinking about the relationships between angles and distances. Once you have the half chord, you have sine. And once you have sine, cosine follows naturally. The cosine is the sine of the complementary angle, the angle that completes the right triangle. If you know one angle in a right triangle, you know the other, because the two non-right angles always add up to 90 degrees. So the sine of one is the cosine of the other. They are two sides of the same relationship, two ways of looking at the same right triangle. But sine and cosine are not the whole story. There is a third function that emerges naturally from the same geometry, and it is called tangent. Tangent is the ratio of the opposite side to the adjacent side in a right triangle. It is the sine divided by the cosine. In the ladder picture, where the ladder leans against a wall, the tangent of the angle at the ground is the height reached divided by the distance of the base from the wall. It tells you the slope of the ladder. A steep ladder has a large tangent. A shallow ladder has a small tangent. Tangent is the measure of steepness. The Islamic scholars who received the Indian half-chord idea recognized the value of tangent and developed it further. Al-Battani, the astronomer who refined the sine, also worked with tangent, using it in his astronomical calculations. He found that tangent was often more convenient than sine for certain types of problems, especially those involving the height of celestial bodies above the horizon. The tangent of an angle is the ratio of the vertical to the horizontal, and in many practical situations, that is exactly the ratio you need. There is a reason tangent behaves differently from sine and cosine. Sine and cosine are confined to values between -1 and +1. They are ratios of sides in a right triangle, and the hypotenuse is always the longest side, so the opposite and adjacent sides are never longer than the hypotenuse. The sine and cosine are always fractions of the hypotenuse, never larger than the hypotenuse itself. But tangent is the ratio of the opposite side to the adjacent side, and the adjacent side can be very small. If the angle is close to 90 degrees, the adjacent side is close to 0, and the tangent grows very large. There is no upper bound on tangent. It can be any positive number, and it can even become infinite in a sense. When the angle reaches 90 degrees, and the adjacent side disappears entirely. This behavior of tangent, its tendency to grow without limit, makes it useful for describing situations where a line becomes nearly vertical. The slope of a line is its tangent. A line with a slope of 1 rises at 45 degrees. A line with a slope of 2 rises more steeply. A line with a slope of 10 is nearly vertical, and a line with an infinite slope is perfectly vertical, rising straight up with no horizontal run at all. Tangent gives us a way to talk about steepness in a single number, a number that covers the entire range from flat to vertical. The Islamic scholars also developed other trigonometric functions, though not all of them have survived in modern use. They worked with secant, cosecant, and cotangent, functions that are less common today, but were useful for certain types of calculations. These functions are reciprocals of the three main functions. Secant is the reciprocal of cosine, cosecant is the reciprocal of sine, cotangent is the reciprocal of tangent. They are not as intuitive as sine and cosine, but they appear in some mathematical contexts, and they were part of the toolkit that Islamic scholars built. The development of trigonometry in the Islamic world was not isolated. It was part of a broader mathematical tradition that included algebra, geometry, and number theory. Scholars worked across these fields, and insights from one area often informed another. Al-Khwarizmi, whose name gave us the word algorithm, was primarily an algebraist, but his work on systematic calculation methods was essential for generating trigonometric tables. The tables that astronomers used required thousands of individual calculations, each one done by hand. Without efficient methods for performing these calculations, the tables would have taken even longer to produce and would have been more prone to errors. The Islamic scholars also made contributions to spherical trigonometry, which is trigonometry applied to the surface of a sphere. Spherical trigonometry is essential for navigation and astronomy, because the Earth and the sky are spherical. The relationships that hold on a flat surface do not hold on a sphere. The angles of a triangle on a sphere add up to more than 180 degrees. The sides of a spherical triangle are measured in degrees rather than in lengths. The rules are different, but they are still trigonometric. Islamic scholars developed methods for solving spherical triangles, which allowed them to calculate the direction to Mecca for prayer, a practical problem that mattered to Muslims around the world. These methods were also useful for navigation, as sailors began to venture farther from familiar shores. The mathematics of spherical trigonometry was a bridge between the flat geometry of the Greeks and the curved geometry of the real world. When European scholars began translating Arabic texts into Latin, they encountered a mature and well-developed body of trigonometric knowledge. The sine and cosine and tangent were already there, with tables and methods for using them. The European scholars did not have to reinvent these ideas. They received them through translation, and they built on them. The first European scholars to work with trigonometry were largely interested in astronomy. They used the tables and methods they had received from the Islamic world to refine their own calculations of planetary positions. But as navigation and surveying became more important, they began to see trigonometry as a practical tool for solving problems on Earth, not just in the sky. The development of trigonometry in Europe was shaped by the needs of the time. Sailors needed to know their latitude and longitude. Surveyors needed to measure land and map coastlines. Engineers needed to design buildings and bridges. Each of these fields required trigonometric calculations, and each field pushed the mathematics in slightly different directions. The German mathematician Regiomontanus, who lived around 550 years before now, was one of the first European scholars to write a comprehensive treatise on trigonometry. He organized the subject systematically, presenting the definitions of sine, cosine, tangent, and the other functions, along with the relationships between them. He included tables of values for use in calculations. His work was a reference for later mathematicians and astronomers. Regiomontanus also recognized that trigonometry could be applied to problems beyond astronomy. He wrote about surveying and navigation, showing how trigonometric methods could be used to measure distances and positions. He was aware that the same mathematics that tracked the stars could also measure the Earth. A century or so after Regiomontanus, the French mathematician François Viète made a more abstract contribution. Viète treated trigonometric relationships as algebraic formulas, not just as geometric constructions. He wrote sine and cosine as symbols that could be manipulated in equations. This was a shift from geometry to algebra, from drawing to calculation. Vieta showed that the relationships between angles and sides could be expressed in terms of symbolic operations, and that these operations could be combined and rearranged, just like any other algebraic expressions. This shift was important because it made trigonometry a part of algebra, not just a separate subject. It meant that trigonometric relationships could be integrated into the broader body of mathematics, and that they could be extended in ways that were not tied to geometric diagrams. Vieta's work was a step toward the modern view of trigonometry as a set of functions, not just a set of measurements. The final step in this direction was taken by Leonhard Euler, the Swiss mathematician who lived in the 18th century. Euler defined sine and cosine in terms of the unit circle, a circle with a radius of exactly 1. On this circle, the sine of an angle is the vertical coordinate of a point on the circle, and the cosine is the horizontal coordinate. These definitions are simple and elegant. They do not require a triangle or a specific radius. They depend only on the angle. The unit circle definition also makes the relationship between sine and cosine clearer. Since the radius is 1, the sine and cosine are just the coordinates of a point moving around the circle. They are the two components of a position vector. The Pythagorean theorem tells us that the square of the sine plus the square of the cosine is always 1, because that is the equation of a circle. This relationship, sine squared plus cosine squared equals 1, is the fundamental identity of trigonometry. It follows directly from the geometry of the unit circle. The unit circle also makes the wave behavior of sine and cosine visible. As a point travels around the circle, its vertical coordinate, the sine, rises and falls in a repeating pattern. The horizontal coordinate, the cosine, does the same thing, but it is shifted by a quarter of the cycle. The sine and cosine are waves, and the unit circle is the source of those waves. This is why trigonometry describes sound and light and the tides. They are all wave phenomena, and waves are described by sine and cosine. The radian, which Euler also introduced, is the natural companion to the unit circle. A radian is the angle subtended by an arc of the circle that is equal in length to the radius. In a unit circle, where the radius is 1, the radian is the angle that corresponds to an arc length of 1. A full circle is 2 pi radians, because the circumference of a unit circle is 2 pi. This is not an arbitrary choice. It is the only choice that makes the derivative relationship simple. In calculus, the derivative of sine with respect to angle is cosine, and the derivative of cosine is negative sine, but only if the angle is measured in radians. If you use degrees, you get factors of pi over 180 that clutter the equations. Radians are the language of advanced trigonometry, and they are the language in which the subject connects to the rest of mathematics. Euler's work was a synthesis of everything that had come before. He took the half-chord from India, the tangent from the Islamic world, the algebraic treatment from Vieta, and the astronomical tradition from the Greeks, and he combined them into a single coherent framework. The unit circle and the radian were the final pieces. After Euler, trigonometry was a complete subject with a clear foundation and a set of relationships that could be applied to any problem involving angles and distances. But the story does not end with Euler. The sine and cosine that he defined in terms of the unit circle turned out to be more than just tools for measuring triangles. They were descriptions of a deeper pattern in the world. They appeared in the motion of pendulums, the vibration of strings, the propagation of sound, and the behavior of light. They were everywhere that things repeated in a regular cycle. The connection between trigonometry and waves was not fully understood until the work of Joseph Fourier, a French mathematician who lived about 200 years before now. Fourier showed that any repeating pattern, no matter how complex, could be built from sine waves. This was a profound insight. It meant that sine and cosine were not just one type of wave among many. They were the building blocks of all periodic behavior. Fourier's discovery was the foundation of modern signal processing. When you record a sound, you are capturing a complex wave pattern. When you compress that recording to store it on a device, you are breaking it down into its sine wave components. keeping only the most important ones and discarding the rest. When you play it back, the device reconstructs the wave from those components. All of this is based on Fourier's insight that sine waves are the basic ingredients of any repeating signal. The same idea applies to images. A photograph is a two-dimensional pattern of light and dark. It can be broken down into sine waves in 2 dimensions. Image compression algorithms, such as those used in JPEG files, rely on this decomposition. They keep the most important sine wave components and discard the ones that are less visible to the human eye. This is why images can be stored in small files without losing too much visual quality. The sine wave decomposition captures the essential structure of the image. Radio transmission also relies on sine waves. A radio signal is a sine wave that has been modified to carry information. The modification might be in the amplitude, the frequency, or the phase of the wave. The receiver decodes these modifications to recover the information. This is how music is broadcast over the air, how television signals reach your screen, and how your phone communicates with a cell tower. The sine wave is the carrier, and trigonometry is the language of the modulation. GPS navigation uses trigonometry in a different way. The satellites that orbit the Earth broadcast signals that include the time and the satellite's position. Your phone receives signals from several satellites and measures the time delay of each signal. The time delay tells you the distance to the satellite. With distances to several satellites, you can triangulate your position. The mathematics of triangulation is trigonometry, applied to the curved surface of the Earth and the 3-dimensional space above it. The same mathematics that locates your phone also locates ships and aircraft. The global positioning system is essentially a large-scale triangulation network, with satellites instead of surveyors' marks. The calculations are done automatically, millions of times a day, using the same sine and cosine that were developed thousands of years ago by people who did not know what a satellite was. The sine and cosine are also present in the design of buildings and bridges. Architects and engineers use them to calculate the forces on a structure. A sloped roof, for example, has a component of its weight that presses downward and a component that pushes outward. The size of each component depends on the angle of the roof. The sine and cosine tell you how much of the weight goes in each direction. This is essential for designing a roof that will not collapse under its own weight or under a load of snow. The same calculations apply to any sloped surface. A ramp, a staircase, a road on a hillside, all of these have angles that determine how forces are distributed. The sine and cosine are the tools that engineers use to turn an angle into a force, a load into a stress, a design into a safe structure. Your own body uses trigonometry, though you are not aware of it. The joints in your body rotate around fixed points, tracing out angles as they move. The muscles that move those joints pull at angles, and the force they generate is divided into components. The sine and cosine describe this division. Physical therapists and biomechanics researchers use trigonometric calculations to understand how the body moves and how it can be injured or healed. Every time you bend your elbow, there is a triangle formed by your upper arm, your forearm, and the line between your shoulder and your wrist. The sine and cosine of the angle at your elbow determine the torque, the twisting force, that your muscles need to generate to hold a weight. This is not something you think about. It is something your body does automatically, but it is governed by the same relationships that the rope stretchers use to lay out a field by the Nile. The trigonometric functions are not just mathematical abstractions, they are descriptions of the way things are. The angle between your spine and the mattress is not just a random position, it is a geometric relationship that has a sine and a cosine. You can measure them if you want to, but you do not need to. They are already there, quietly doing their work, whether you notice them or not. If you shift your position slightly, the angles change, and the sine and cosine change with them. The relationship between the angle and the ratio is fixed. It is the same for everyone, everywhere, at all times. It does not depend on who you are or where you are. It is a property of the geometry of space itself. That is what trigonometry is, ultimately. a description of the relationships that hold between angles and distances in the world. The relationships are old. They were worked out slowly, over thousands of years, by people who did not know they were building a subject. They were just trying to measure fields and track stars and navigate ships. But the relationships they found turned out to be universal. They apply to the smallest joint in your body and to the largest orbit in the solar system. They apply to the sound of a voice and to the light from a star. They apply to the angle of the light falling across the ceiling and to the angle of the Earth's axis as it tilts toward the sun. It is a quiet thing to be surrounded by mathematics that you do not have to think about. The sine and cosine are in the room with you now. They are in the position of your body and in the light on the ceiling. They are in the sound of your breathing and in the rhythm of your heart. They have been here the whole time, and they will be here long after you have fallen asleep. The sine and cosine, as they were understood by the end of the Islamic period, were practical tools. They were things you could look up in a table, values associated with specific angles, numbers that let you convert a measured angle into a distance or a height. They were useful and they were used by astronomers and surveyors and navigators. But they were still tied to the geometry of the circle. The sine of an angle was a length, a segment of a chord, a measurable quantity in a drawn figure. It was not yet an abstract function, a rule that existed independently of any particular circle. The shift from geometry to algebra, from drawn figures to symbolic equations, happened gradually over the course of the 16th and 17th centuries. It was part of a larger movement in European mathematics, a movement toward abstraction and generalization. Mathematicians began to see that the relationships they had been working with geometrically could be expressed in algebraic form, using symbols and equations, and that this algebraic form was more powerful and more flexible than the geometric form. The French mathematician François Viète was one of the early figures in this movement. He lived in the 16th century, around 450 years before now, and he made significant contributions to algebra, trigonometry, and other fields. In trigonometry, Viète introduced a new way of thinking about sine and cosine. He treated them as functions, as rules that take an angle as input and produce a number as output. He wrote them in algebraic notation, using symbols rather than geometric diagrams. This might sound like a small change, a matter of notation rather than substance, but it was not. The shift to algebraic notation meant that sine and cosine could be manipulated in equations, combined with other functions, and extended in ways that were not tied to the geometry of the circle. Viète showed that the relationships between sine and cosine could be expressed as algebraic identities, and that these identities could be used to derive new relationships. He was moving trigonometry from a practical measuring technique to a branch of abstract mathematics. Viète's work was followed by others, including the English mathematician Thomas Harriot and the Scottish mathematician John Napier, both of whom contributed to the development of trigonometry in the late 16th and early 17th centuries. Napier is best known for his invention of logarithms, which were a powerful tool for simplifying calculations. Logarithms turn multiplication into addition, and they were widely used by astronomers and navigators who had to perform many tedious calculations. Napier's work on logarithms was closely connected to trigonometry, because many of the calculations that astronomers performed involved sine and cosine values. The development of logarithms was a practical advance, but it also had a conceptual dimension. Logarithms are functions, rules that take a number and produce another number. They are abstract, not tied to any particular physical situation. The success of logarithms helped to establish the idea that mathematical functions could be studied for their own sake, not just as tools for solving practical problems. The 17th century saw further developments in trigonometry, including the introduction of the sine and cosine as infinite series. An infinite series is a sum of infinitely many terms that approaches a limit. The sine of an angle, for example, can be expressed as an infinite series of powers of the angle, with alternating sines and specific coefficients. This representation was developed by mathematicians such as Isaac Newton and Gottfried Leibniz, who were also developing calculus at the same time. The infinite series representation of sine and cosine was a significant advance. It meant that sine and cosine could be calculated for any angle, not just the ones that had been tabulated in tables. It also connected trigonometry to calculus, because the series representation made it possible to differentiate and integrate sine and cosine in a straightforward way. The derivative of sine is cosine, and the derivative of cosine is negative sine. These relationships are simple and elegant, and they are the foundation of the use of sine and cosine in physics. The 18th century brought the work of Leonhard Euler, who synthesized and extended the developments of the previous centuries. Euler's contribution to trigonometry was not just a single result, but a comprehensive reorganization of the subject. He defined sine and cosine in terms of the unit circle, he introduced the radian as the natural unit of angle measurement, and he showed how sine and cosine connect to the rest of mathematics, including the exponential function. The unit circle definition is simple and powerful. It makes sine and cosine the coordinates of a point on a circle of radius 1. This definition removes any dependence on a particular triangle or a particular circle. It makes sine and cosine functions of the angle alone, pure and abstract. The angle is measured in radians, which means that the angle itself is defined in terms of the arc length on the unit circle. A full circle is 2 pi radians, a half circle is pi radians, and a quarter circle is pi over 2 radians. These are not arbitrary choices, they are dictated by the geometry of the circle itself. The connection to the exponential function is one of Euler's most beautiful contributions. He showed that the exponential function with an imaginary argument is equal to the sum of sine and cosine. This relationship, known as Euler's formula, is one of the most important identities in all of mathematics. It connects two apparently different areas, exponential growth and circular motion. It shows that they are the same thing, viewed from different perspectives. Euler's formula is often written as e to the power of I theta equals cosine theta plus I sine theta. The letter e represents the base of the natural logarithm, about 2.718. The letter I represents the square root of -1, the imaginary unit. Theta represents an angle measured in radians. The formula says that the exponential function with an imaginary argument rotates a point around the unit circle. The real part of the exponential is cosine, and the imaginary part is sine. This is a deep and unexpected connection, and it has far-reaching implications. The connection between exponential growth and circular motion is not something that is immediately obvious. Exponential growth is a steady increase, a constant rate of change. Circular motion is a repeating cycle, a return to the starting point. These seem like different things, but Euler's formula shows that they are two aspects of the same underlying process. Exponential growth, when extended to imaginary numbers, becomes circular motion. The sine and cosine are the shadows of that motion. This connection has practical implications as well. It is the foundation of the use of complex numbers in engineering and physics. Electrical engineers use complex numbers to describe alternating current, because the current and voltage in an AC circuit are sine waves, and sine waves are conveniently represented as the real and imaginary parts of a complex exponential. This representation simplifies the mathematics of circuits, making it possible to analyze complex systems using algebra rather than calculus. The same idea applies to quantum mechanics, where the state of a particle is described by a complex wave function. The wave function oscillates in time and space, and its behavior is governed by sine and cosine. The mathematics of quantum mechanics is built on the same trigonometric functions that the rope stretchers used to lay out fields. It is a remarkable continuity, a thread that runs from the mud of the Nile to the equations that describe the smallest things in the universe. The development of trigonometry in the modern period has been shaped by these connections to other fields. Trigonometry is no longer just a tool for measuring triangles. It is part of the broader structure of mathematics, connected to algebra, calculus, complex analysis, and differential equations. It is used in physics, engineering, computer science, and many other fields. It is a language for describing the world, a way of expressing the relationships that hold between angles and distances, between waves and oscillations, between circular motion and periodic behavior. The sine and cosine that you might have encountered in a classroom are the result of this long history. They are not arbitrary definitions. They are the end point of a process that began with a knotted rope on the Nile, continued through clay tablets in Babylon, through astronomical tables in Greece and India, through translations and syntheses in the Islamic world, through algebraic reformulations in Europe, and through the unifying vision of Euler. Each step in this process refined and extended the previous steps, adding new layers of meaning and new applications. The sine and cosine are still being extended and refined today. Mathematicians continue to study their properties, looking for new identities and new connections. Computer scientists continue to develop faster and more accurate methods for computing their values. Engineers continue to find new applications for them in the design of systems and structures. The sine and cosine are not old ideas that have been fully explored. They are living ideas, still growing and changing, still being used in new ways. If you have ever used a calculator to find the sine of an angle, you have benefited from this long history. The calculator does not use a table of chords or a geometric construction. It uses an algorithm, a series of arithmetic operations that approximate the sine to the desired accuracy. The algorithm is based on the infinite series representation of sine, which was developed in the 17th century. It is a product of centuries of work, distilled into a few lines of code. If you have ever listened to music, you have heard the sine wave. Every sound is a combination of sine waves, and the character of the sound depends on the combination. The sine wave is the basic building block of sound, just as the point on the unit circle is the basic building block of trigonometry. The connection between the two is direct and real. The sine and cosine are also present in the natural world. The tides rise and fall in a pattern that is approximately sinusoidal. The seasons change in a pattern that is driven by the sinusoidal variation of the sun's height above the horizon. The length of the day varies sinusoidally over the course of the year. The positions of the planets are governed by the same trigonometric functions that Hipparchus used to build his table of chords. The sine and cosine are everywhere, and they have been everywhere for a long time. The rope stretchers did not know that they were using sine and cosine, but they were using the relationships that sine and cosine describe. The Babylonian scribes did not know that they were exploring trigonometric triples, but they were. The Greek astronomers did not know that they were building the foundations of a subject that would outlast their cosmology, but they were. It is a quiet thing to be part of this history. You are lying in a room surrounded by angles and distances, and those angles and distances are governed by relationships that have been understood for thousands of years. The sine and cosine are working in the background, in the structure of the room, in the sound of the air, in the light on the ceiling. They have been working for thousands of years, and they will keep working after you have fallen asleep. The sine and cosine are not just buttons on a calculator. They are descriptions of something real. They are the language of angles and distances, of waves and cycles, of motion and change. They are the mathematics of the world, and they are here with you now, in the dark, in the quiet, in the stillness of the room. There is a quiet shift that happens when you move from thinking about trigonometry as a collection of triangles to thinking about it as a description of circular motion. The triangles are still there, they do not go away, but they become part of a larger picture, a picture that includes circles and waves and repeating patterns of all kinds. The sine and cosine, which started as ratios of sides in right triangles, become coordinates of a point moving around a circle. And once you see them that way, you start to see them everywhere. The unit circle is the key to this shift. It is a circle with a radius of exactly 1, centered at a fixed point. On this circle, every point has a position that can be described by two numbers. The horizontal position is cosine, The vertical position is sine. These numbers change as the point moves around the circle, and they change in a regular, predictable way. They are not arbitrary. They are determined by the angle that the point has traveled from its starting position. The starting position is usually taken to be the point on the far right of the circle, the point directly to the right of the center. From there, the point moves counterclockwise, tracing out the circle as it goes. As it moves, the angle at the center grows. The angle is measured from the starting position, from the horizontal line that points to the right. When the point has moved a little way, the angle is small. When it has moved a quarter of the way around the circle, the angle is 90 degrees, or pi over 2 radians. When it has moved halfway around, the angle is 180 degrees, or pi radians. And when it has moved all the way around, the angle is 360 degrees, or 2 pi radians. At each position along the way, the point has a sine and a cosine. The sine is the vertical distance from the center to the point. The cosine is the horizontal distance from the center to the point. These distances are measured in the same units as the radius, and since the radius is 1, the sine and cosine are simply the coordinates of the point. They are numbers between -1 and +1, because the point never moves farther from the center than the radius allows. When the point is at the starting position, on the far right, its vertical distance from the center is 0, so its sine is 0. Its horizontal distance from the center is 1, so its cosine is 1. As the point moves upward along the circle, its sine increases because it is getting higher, and its cosine decreases because it is moving leftward, away from the far right position. At the top of the circle, the point is directly above the center. Its sine is 1, its maximum value, and its cosine is 0. As the point continues down the left side of the circle, its sine decreases back towards 0, and its cosine becomes negative, because the point is now to the left of the center. At the far left of the circle, the point is directly to the left of the center. Its sine is 0, and its cosine is -1. As the point moves down the lower half of the circle, its sine becomes negative, because the point is below the center, and its cosine increases back towards 0. At the bottom of the circle, the point is directly below the center. Its sine is -1, and its cosine is 0, and as the point moves back up the right side of the circle, its sine increases back toward 0, and its cosine increases back toward 1, until it reaches the starting position again. This cycle repeats forever. The point keeps moving, and the sine and cosine keep oscillating between their maximum and minimum values. They are periodic functions, meaning they repeat their values at regular intervals. The interval is one full revolution around the circle, an angle of 2 pi radians. After that, the sine and cosine are back to their starting values, ready to do the same thing again. The sine and cosine are not just numbers. They are descriptions of a process, a motion. They tell you where the point is at any moment, and they tell you how it is moving. The sine tells you the vertical position. The cosine tells you the horizontal position. Together, they give you the complete position of the point, and because the point is moving at a constant speed around the circle, the sine and cosine change smoothly and continuously. There are no jumps, no sudden changes. The motion is regular and predictable. This is why the sine and cosine are useful for describing waves. A wave is a repeating pattern, a motion that goes back and forth or up and down in a regular cycle. The sine and cosine are the mathematical description of that kind of motion. They give you the position of something that is oscillating, that is moving in a cycle, at any time. Think of a weight hanging from a spring. If you pull the weight down and let it go, it will bounce up and down. The motion is periodic. It goes down, then down again, in a regular rhythm. The position of the weight over time is a sine wave, or a cosine wave, depending on where you start measuring. The sine and cosine describe that motion exactly. Think of a pendulum swinging back and forth. The same thing happens. The pendulum swings one way, then the other, then back again. The angle of the pendulum over time is a sine wave. The sine and cosine describe the motion of the pendulum, just as they describe the motion of the point on the unit circle. Think of a guitar string that has been plucked. The string vibrates back and forth, producing sound. The vibration of the string is a sine wave, or a combination of sine waves. The sine and cosine describe the shape of the string as it vibrates, and they describe the sound that the string produces. The sine and cosine are everywhere that things repeat. They are the language of repetition, the mathematics of cycles. They describe the motion of the planets, the rise and fall of the tides, the changing of the seasons. They describe the sound of a voice and the light from a star. They describe the beating of your heart and the rhythm of your breathing. Once you have the unit circle, you also have a way to define the other trigonometric functions. The tangent is the ratio of sine to cosine. On the unit circle, the tangent has a geometric interpretation as well. If you draw a line tangent to the circle at the far right point, and you extend the radius through the moving point until it intersects that tangent line, the length of the segment from the tangent point to the intersection is the tangent of the angle. This is a less direct interpretation than the sine and cosine, but it is consistent with the ratio definition. The tangent grows without bound as the angle approaches 90 degrees, because the radius line becomes parallel to the tangent line and never intersects it. There are also the reciprocal functions, secant, cosecant, and cotangent. These are less commonly used today, but they have their place in certain contexts. The secant is the reciprocal of cosine. The cosecant is the reciprocal of sine. The cotangent is the reciprocal of tangent. They are defined in terms of the unit circle in the same way that the tangent is defined, by extending lines and measuring segments. The unit circle also gives a clear way to understand the relationships between the trigonometric functions. The identity that sine squared plus cosine squared equals 1 follows directly from the Pythagorean theorem applied to the right triangle formed by the radius, the sine, and the cosine. The radius is 1, so the square of the sine plus the square of the cosine is 1. This is a fundamental relationship, one that holds for any angle. The angle addition formulas also have a geometric interpretation on the unit circle. If you add two angles, the sine and cosine of the sum can be expressed in terms of the sines and cosines of the individual angles. These formulas are not just algebraic identities. They describe the geometry of the circle, the way that rotations combine. The unit circle is a rich source of insight. It connects trigonometry to geometry in a direct and intuitive way. It makes the functions visible, not just as symbols on a page, but as coordinates of a moving point. It shows why the sine and cosine are periodic, why they oscillate, why they are useful for describing waves. It makes the subject concrete and tangible. The unit circle also connects trigonometry to complex numbers. A complex number is a number that has two parts, a real part and an imaginary part. It can be written as a plus b times I, where I is the square root of -1. The complex numbers can be represented as points on a plane, with the real part on the horizontal axis and the imaginary part on the vertical axis. This is exactly the same as the unit circle representation of sine and cosine, except that the circle is not confined to the unit radius. Any complex number corresponds to a point on the complex plane, and its position can be described by its distance from the origin and its angle from the horizontal axis. The distance from the origin is called the modulus, and the angle is called the argument. The sine and cosine of the argument, multiplied by the modulus, give the real and imaginary parts of the complex number. This is the connection between trigonometry and complex numbers. The sine and cosine are the bridge between the geometry of the circle and the algebra of complex numbers. This connection is more than just a curiosity. It has practical applications. In electrical engineering, alternating current is described using complex numbers. The current and voltage in an AC circuit are sine waves, and they are conveniently represented as the real and imaginary parts of a complex number. The circuit analysis is done using complex arithmetic, which is simpler than working with trigonometric functions directly. The sine and cosine are still there, underneath the complex notation, but they are hidden. In quantum mechanics, The state of a particle is described by a complex wave function. The wave function oscillates in time and space, and its behavior is governed by sine and cosine. The complex representation is natural for quantum mechanics because it allows the wave function to have both amplitude and phase. The amplitude is the modulus and the phase is the argument. The sine and cosine are the components of the wave function. In signal processing, the Fourier transform is used to analyze signals. The Fourier transform decomposes a signal into its frequency components. Each frequency component is a sine wave, or a complex exponential, which is a combination of sine and cosine. The Fourier transform is a fundamental tool in communications, audio processing, image processing, and many other fields. It is built on the connection between trigonometry and complex numbers. The unit circle is a simple object, but it is connected to a vast web of ideas. It is the source of the sine and cosine, and the sine and cosine are the source of many of the mathematical tools that we use to describe the world. The circle, the wave, the complex plane, the Fourier transform, these are all connected through the same set of relationships. If you have ever used a computer to process an image, or a phone to play music, or a GPS to find your way, you have used trigonometry. The sine and cosine are behind these technologies, hidden from view but essential to their operation. They are the quiet mathematics of the modern world, the foundation on which much of our technology is built. The unit circle is also a reminder of the continuity of mathematics. The same ideas that were developed by rope stretchers and Babylonian scribes and Greek astronomers and Indian mathematicians and Islamic scholars and European mathematicians are still in use today. They have been refined and extended, but they are still the same ideas. The sine and cosine that you might have learned in school are the sine and cosine that Hipparchus tabulated, that Aryabhata named, that Euler defined. They are the same functions, with the same properties, the same relationships. It is a quiet thing to be connected to this history. The sine and cosine are not just abstract symbols. They are the product of thousands of years of human effort, the accumulated wisdom of many cultures. They are a testament to the persistence of human curiosity, the desire to understand the patterns of the world. And they are still here, still useful, still growing, still being discovered anew by each generation. The unit circle is a place to rest. It is a simple image, a point moving around a circle, but it contains a great deal. It contains the sine and cosine, the tangent and the secant, the relationships between them, the connection to complex numbers, the foundation for wave analysis. It is a starting point for understanding a large part of mathematics and physics. If you find yourself drifting, let the image of the unit circle carry you. Picture the point, moving slowly around the edge of the circle, tracing out its path. Watch the sine rise and fall. Watch the cosine shift from positive to negative and back again. Let the rhythm of the motion settle into you, the way a gentle wave can settle into a shore. There is no need to hold on to the details. The image is enough, the point, the circle, the two shadows. That is the whole thing, held in one picture. The sine and cosine, once they are understood as coordinates on the unit circle, begin to reveal their true nature. They are not just ratios in a triangle, they are descriptions of motion. A point moving around a circle traces out a path that can be described by two numbers, one that tells you how far up or down the point is, and one that tells you how far left or right. These numbers change smoothly as the point moves, and they repeat themselves every time the point completes a full circuit. This repetition is what makes the sine and cosine periodic, and periodicity is what connects them to the world of waves. If you take the sine and stretch it out over time, rather than over the angle around a circle, you get a wave. The sine wave is a smooth, regular oscillation. It rises to a peak, falls to a trough, and rises again, over and over, at a steady rate. This shape appears everywhere. It is the shape of a vibrating string. It is the shape of a pendulum swinging. It is the shape of the tide, coming in and going out. It is the shape of the seasons changing, of the day lengthening and shortening, of the moon waxing and waning. The sine wave is the pattern of repetition, the shape of a cycle. The cosine is the same wave, just shifted. If you start measuring a sine wave at the point where it crosses zero, it rises to a peak, falls to a trough, and returns to zero. If you start measuring a cosine wave at the point where it is at a peak, it falls to zero, goes to a trough, returns to zero, and rises to a peak. The cosine is the sine shifted by a quarter of a cycle. They are the same shape, just offset from each other in time. This offset is called a phase shift, and it is one of the key ideas in understanding how waves combine and interact. The sine wave has a few basic properties that are worth holding on to. The height of the wave is called its amplitude. The distance from one peak to the next is called its wavelength, or its period, depending on whether you are looking at space or time. The speed at which the wave repeats is called its frequency. These properties are all connected. A wave with a high frequency repeats quickly. A wave with a low frequency repeats slowly. A wave with a large amplitude has tall peaks and deep troughs. A wave with a small amplitude is flatter, closer to a straight line. In the unit circle, the amplitude is always 1, because the radius of the circle is 1. The point on the circle never moves farther from the center than 1 unit, so the sine and cosine never exceed 1 in absolute value. But in the physical world, waves can have any amplitude. A loud sound has a larger amplitude than a soft sound. A bright light has a larger amplitude than a dim light. The amplitude of a wave is a measure of its strength, its intensity, how much energy it carries. The frequency of a wave in the unit circle is tied to the speed of the point moving around the circle. If the point moves quickly, it completes a full circle in a short time, and the sine and cosine repeat quickly. If the point moves slowly, the repetition is slow. In the physical world, frequency is what we hear as pitch. A high-pitched sound is a high-frequency wave. A low-pitched sound is a low-frequency wave. The frequency of a light wave is what we see as color. A high-frequency light is toward the blue end of the spectrum. A low-frequency light is toward the red end. The sine wave is the basic building block of many physical phenomena, but real-world waves are rarely pure sine waves. A pure sine wave is a perfect, unvarying oscillation, like the sound of a tuning fork. Most sounds are more complex. They are combinations of sine waves of different frequencies and amplitudes, layered together. This is where the work of Joseph Fourier becomes important. Fourier, a French mathematician working about 200 years ago, showed that any repeating pattern can be built from sine waves. The pattern might be complicated, jagged, irregular, but if it repeats, it can be decomposed into a set of sine waves of specific frequencies and amplitudes. This is a powerful result. It means that the sine wave is not just one type of wave among many. It is the fundamental ingredient from which all other repeating patterns are made. The decomposition of a pattern into sine waves is called a Fourier series. The Fourier series of a repeating pattern tells you which sine waves are present and how much of each one is there. This is useful for many reasons. It lets you analyze a complicated sound to see what frequencies it contains. It lets you compress a signal by keeping only the most important frequencies and discarding the rest. It lets you filter a signal, removing unwanted frequencies and keeping the ones you want. The Fourier series is the foundation of much of modern signal processing. When you listen to a digital music file, the file is stored as a set of numbers that represent the amplitudes of different frequencies. The player reconstructs the sound from those numbers. When you take a photograph with a digital camera, the image is stored as a set of frequency components. The viewer reconstructs the image from those components. When you use a cell phone, the voice signal is broken down into frequencies, transmitted, and reconstructed at the other end. All of this is based on Fourier's insight that sine waves are the building blocks of repeating patterns. The Fourier series is not just a theoretical idea, it is a practical tool, and it is used constantly in engineering and science. Electrical engineers use it to design circuits that filter signals. Audio engineers use it to equalize sound, boosting some frequencies and cutting others. Medical imaging uses it to reconstruct images from scans. The list goes on. The Fourier series is one of the most useful tools in applied mathematics, and it is built entirely on the sine and cosine. The sine and cosine are not just mathematical abstractions, they are real, physical things. They are the shape of a sound wave, the pattern of a light wave, the oscillation of a pendulum, the vibration of a string. They are everywhere in the natural world, and they are everywhere in the technology that we use every day. They are the mathematics of repetition, the language of cycles. The connection between the unit circle and the sine wave is direct. The unit circle gives you the sine and cosine as coordinates of a moving point. The sine wave is the graph of those coordinates over time. If you watch the point moving around the circle and you record its height at each moment, you get a sine wave. If you record its horizontal position, you get a cosine wave. The circle and the wave are the same thing, seen from two perspectives. The circle is the geometry. The wave is the graph. They are connected by the motion of the point. This connection is one of the reasons that trigonometry is so powerful. It lets you move between geometry and graphs, between circles and waves, between angles and frequencies. The sine and cosine are the bridge between these different ways of seeing the world. They are the translators, the interpreters, the links between the static and the dynamic. The sine and cosine also connect to the concept of resonance. Resonance occurs when a system is driven at its natural frequency. A pendulum has a natural frequency, determined by its length. If you push the pendulum at that frequency, it swings higher and higher. If you push at a different frequency, it does not swing as high. This is resonance. The same thing happens with sound, with light, with electrical circuits, with many physical systems. The sine and cosine describe the natural oscillations of these systems, and they describe the response of the systems to external driving forces. Resonance is important in many contexts. It is how a radio works. The radio receiver is tuned to a specific frequency, the frequency of the station you want to listen to. Other frequencies are ignored. The receiver is resonant at that frequency. It is also how a musical instrument works. The body of a guitar resonates at certain frequencies, amplifying those frequencies and giving the guitar its characteristic sound. The sine and cosine are the mathematics of resonance. They describe the frequencies that a system responds to. The sine and cosine also describe interference. When two waves meet, they add together. If they are in phase, meaning their peaks and troughs align, they reinforce each other. The combined wave is larger. If they are out of phase, meaning a peak meets a trough, they cancel each other out. The combined wave is smaller. This is interference, and it is described by the sine and cosine. The addition of two sine waves is another sine wave, with a phase shift and an amplitude that depend on the original waves. The mathematics of interference is the mathematics of adding sines and cosines. Interference is everywhere. It is how noise-canceling headphones work. They produce a wave that is out of phase with the background noise, canceling it out. It is how holograms work. They record the interference pattern of two light waves and reconstruct the image by playing that pattern back. It is how the colors of a soap bubble are produced. The light reflecting from the front and back surfaces of the bubble interferes, producing colors. The sine and cosine describe all of these phenomena. The sine and cosine are also the basis of the Fourier transform, which is a generalization of the Fourier series. The Fourier transform takes a signal and breaks it down into its frequency components. It is used in many fields, from physics to engineering to finance. It is a powerful tool for analyzing data, for finding patterns, for extracting information from noisy signals. The Fourier transform is built on the sine and cosine, and it is one of the most important tools in modern science. The sine and cosine are not just mathematical functions, they are descriptions of the way the world works. They describe the motion of the planets, the vibration of atoms, the propagation of light. They describe the sound of a voice, the color of a flower, the rhythm of a heartbeat. They are the mathematics of nature, the language of the universe. And they are here with you now, in the quiet of the room, in the stillness of the night. The sine and cosine are in the sound of your breathing, in the rhythm of your heart, in the gentle rise and fall of your chest. They are in the light that falls across the ceiling, in the pattern of shadows, in the angle of your body against the mattress. They have been here the whole time, quietly doing their work, and they will be here long after you have fallen asleep. The sine and cosine are not something you need to hold on to. They are something you can let go of. Trust to be there, the way you trust the ground beneath you or the air around you. They are part of the fabric of things, part of the structure of the world. They are the mathematics of the quiet, the mathematics of the dark, the mathematics of the long, slow cycle of the night. The sine wave is a simple shape. It rises and falls in a smooth, regular pattern. It is the shape of a pure tone, the sound of a tuning fork, the motion of a pendulum swinging through a small arc. It is the shape of a weight bouncing on a spring, the shape of a plucked guitar string, the shape of the tide as it comes in and goes out. It is the shape of the day lengthening and shortening over the course of a year, the shape of the moon's phases, the shape of the Earth's orbit around the sun. But the world is not made of pure sine waves. The world is made of complicated patterns, patterns that are built from many sine waves layered together. A human voice is not a pure tone. It is a combination of many tones, each with its own frequency and amplitude. A musical instrument is not a pure tone. It is a combination of a fundamental frequency and a set of overtones, harmonics that give the instrument its characteristic sound. The light from a star is not a pure wave. It is a combination of many frequencies spread across the spectrum. The insight that complicated patterns can be built from simple sine waves is one of the most useful ideas in mathematics and science. It was developed by Joseph Fourier, a French mathematician who lived about 200 years ago. Fourier was studying heat flow, but his work turned out to have applications far beyond that. He showed that any repeating pattern, no matter how complex, can be expressed as a sum of sine waves of different frequencies and amplitudes. This is a powerful result. It means that you can analyze a complicated pattern by breaking it down into its constituent sine waves. You can find out which frequencies are present and how much of each frequency there is. This analysis is called a Fourier analysis, and it is used in many fields. It is used to analyze sound, to compress images, to filter signals, to understand the structure of data. It is one of the most important tools in applied mathematics. The Fourier analysis of a sound tells you the frequencies that make up that sound. A pure tone has a single frequency. A human voice has many frequencies, spread across a range. The pattern of frequencies is what gives the voice its character, its quality, its identity. You can recognize a voice because you have heard its frequency pattern before. You can recognize a musical instrument because you are familiar with its pattern of overtones. The Fourier analysis of an image tells you the spatial frequencies that make up that image. A smooth, uniform area has low spatial frequencies. A sharp edge has high spatial frequencies. The pattern of spatial frequencies is what gives the image its detail, its texture, its content. Image compression algorithms work by keeping the most important spatial frequencies and discarding the rest. This is how a JPEG file can be much smaller than the original image, while still looking almost the same. The Fourier analysis of a signal tells you the frequency content of that signal. This is useful for many purposes. You can filter out unwanted frequencies, such as noise. You can enhance desired frequencies, such as the signal you are trying to detect. You can analyze the behavior of a system by looking at its frequency response. The Fourier transform is a fundamental tool in signal processing. The sine wave is the building block of the Fourier analysis. It is the simplest repeating pattern, and it is the ingredient from which all other repeating patterns are made. The Fourier analysis is a way of taking a pattern apart into its building blocks. It is a way of seeing the structure of something that looks complex. The Fourier analysis is also a way of synthesizing patterns. If you know the frequencies and amplitudes of the sine waves that make up a pattern, you can reconstruct the pattern by adding them together. This is how a digital music player works. The player reads a file that contains the frequency information, and it reconstructs the sound by adding together the sine waves. This is how a digital camera works. The camera captures the frequency information of an image, and the viewer reconstructs the image by adding together the sine waves. The Fourier analysis is a two-way street. You can take a pattern apart into its frequencies, and you can put it back together from those frequencies. This is what makes it so useful. It gives you a way to represent a pattern in a different form, a form that is often more convenient for analysis, storage, or transmission. The Fourier analysis is built on the sine and cosine. The sine and cosine are the basis functions of the Fourier transform. They are the ingredients from which everything else is made. The Fourier transform decomposes a signal into sine and cosine components. The sine components correspond to the odd part of the signal, and the cosine components correspond to the even part. The combination of sine and cosine gives the complete frequency content. The Fourier transform is not just a theoretical idea. It is a practical tool that is used every day in many fields. It is used in audio engineering, to equalize sound, to remove noise, to add effects. It is used in telecommunications, to modulate and demodulate signals, to multiplex and demultiplex channels. It is used in medical imaging, to reconstruct images from scans, to analyze brain activity. It is used in astronomy, to analyze the light from stars, to detect planets, to study the structure of the universe. The Fourier transform is also used in the study of the Earth. Seismologists use it to analyze the vibrations of the Earth, to study earthquakes, to understand the structure of the planet. Oceanographers use it to analyze waves, to study the tides, to understand the currents. Meteorologists use it to analyze weather patterns, to predict storms, to understand the atmosphere. The Fourier transform is used in finance, to analyze the behavior of markets, to detect trends, to model risk. It is used in economics, to study the cycles of the economy, to understand the factors that drive growth and recession. It is used in biology, to analyze the rhythms of life, to study the cycles of the body, to understand the patterns of health and disease. The Fourier transform is everywhere. It is one of the most important mathematical tools ever developed, and it is built on the sine and cosine. The sine and cosine, which started as ratios of sides in right triangles, have become the foundation of a vast range of modern technology. They are the mathematics of waves, the language of cycles, the basis of the Fourier transform. The sine and cosine are not just mathematical functions. They are descriptions of the way the world works. They describe the motion of the planets, the vibration of atoms, the propagation of light. They describe the sound of a voice, the color of a flower, the rhythm of a heartbeat. They are the mathematics of nature, the language of the universe. And they are here with you now, in the quiet of the room, in the stillness of the night. The sine and cosine are in the sound of your breathing, in the rhythm of your heart, in the gentle rise and fall of your chest. They are in the light that falls across the ceiling, in the pattern of shadows, in the angle of your body against the mattress. They have been here the whole time, quietly doing their work, and they will be here long after you have fallen asleep. The sine and cosine are not something you need to hold on to. They are something you can let go of, trust to be there, the way you trust the ground beneath you or the air around you. They are part of the fabric of things, part of the structure of the world. They are the mathematics of the quiet, the mathematics of the dark, the mathematics of the long, slow cycle of the night. If you find yourself drifting, let the image of the Fourier transform carry you. Picture a complicated pattern, a sound, an image, a signal. Imagine it being broken down into its sine wave components, each one a pure, simple oscillation. Imagine those components being separated, analyzed, understood. And imagine them being put back together, the pattern reconstructed, the complexity restored. This is the Fourier transform. It is a way of seeing the structure in complexity, of finding the simple patterns that underlie the complicated ones. The sine wave is the simple pattern. The Fourier transform is the way of finding it, and the sine and cosine are the tools that make it possible. They are the mathematics of the wave, the language of the cycle, the foundation of the Fourier transform, and they are here with you now, in the quiet of the room, in the stillness of the night. The sine and cosine, once they are understood as the building blocks of the Fourier transform, begin to appear in places that seem to have nothing to do with triangles or circles or waves. They appear in the way your phone compresses a photograph. They appear in the way a radio tuner selects one station from the hundreds that fill the air around you. They appear in the way a satellite sends a signal from orbit to the ground, and in the way that signal is decoded into a voice or a stream of data. The Fourier transform is not the only application of trigonometry in modern technology. It is one of the most important, but it is part of a larger family of techniques that all rely on the same fundamental relationships. The sine and cosine are the common thread, the shared language that runs through signal processing, communications, imaging, and many other fields. Consider the problem of locating a position on the surface of the Earth. This is a problem that has been solved in many ways over the centuries, but the modern solution, the global positioning system, relies on trigonometry at every step. The GPS satellites orbit the Earth at known positions, broadcasting signals that include the time and the satellite's location. Your phone or receiver picks up these signals and measures the time delay between when the signal was sent and when it was received. That time delay, multiplied by the speed of light, gives the distance to the satellite. With distances to several satellites, your phone can calculate its position. This is triangulation, the same technique that surveyors have used for centuries, but applied to 3 dimensions and using satellites instead of landmarks. The mathematics of triangulation is trigonometry. Given the positions of the satellites and the distances to them, you can calculate your own position by solving a set of trigonometric equations. This is done automatically, dozens of times a second, without you ever needing to think about it. The GPS system is a remarkable achievement. It is a global network of satellites, ground stations, and receivers, all working together to provide precise positioning information to anyone with a receiver. It relies on accurate clocks, on the propagation of radio waves, and on the mathematics of trigonometry. The sine and cosine are embedded in the calculations that determine your latitude, your longitude, and your altitude. They are the mathematics of location, the language of position. The same trigonometric relationships are used in navigation more generally. A ship at sea, an aircraft in flight, a car on a road. All of these can be guided by trigonometric calculations. The angle of the sun above the horizon, the angle of a star relative to the North Pole, the angle between the direction of travel and a known landmark, all of these angles can be converted into positions using sine and cosine. Trigonometry is the language of navigation, the tool that lets you know where you are and where you are going. Consider the problem of building a structure that will stand up to the forces of nature. A building, a bridge, a dam, all of these must be designed to resist the forces that act on them. The forces are not always vertical. Wind pushes sideways. Earthquakes shake in all directions. The weight of the structure itself is distributed at various angles. To design a structure that can withstand these forces, engineers must understand how forces combine and how they are transmitted through the structure. The sine and cosine are the tools that engineers use to analyze forces. A force that acts at an angle can be broken down into 2 components, one vertical and one horizontal. The sine of the angle gives the vertical component, and the cosine gives the horizontal component. This is the same idea that we used with the ladder leaning against the wall. The force on the ladder is broken down into a force that pushes against the wall and a force that presses into the ground. The same mathematics applies to a roof beam, a bridge cable, a suspension tower. The sine and cosine tell you how much of the force goes in each direction. This is essential for designing safe structures. If you do not know how much of a force is horizontal, you cannot design a foundation that will resist it. If you do not know how much is vertical, you cannot design a column that will support it. The sine and cosine give you the information you need. They turn an angled force into its two perpendicular components. They are the mathematics of stability, the language of strength. Consider the problem of understanding the motion of the Earth around the Sun. The Earth's orbit is an ellipse, but it is close to a circle. The Earth moves around the Sun in a regular, repeating cycle. The position of the Earth at any time can be described using sine and cosine. The angle of the Earth relative to the Sun, the time of year, the length of the day, all of these can be calculated using trigonometry. The seasons are a trigonometric phenomenon. The Earth's axis is tilted relative to its orbit, so the Sun's height above the horizon changes over the course of the year. When the Sun is high, the days are longer and the weather is warmer. When the Sun is low, the days are shorter and the weather is cooler. The height of the Sun at noon on any given day can be calculated using sine and cosine. The length of the day can be calculated using sine and cosine. The changing of the seasons is a trigonometric process. The tides are also a trigonometric phenomenon. The moon and the sun exert gravitational forces on the Earth's oceans, creating a bulge of water that moves around the Earth as the moon and sun move. The height of the tide at any time and place can be calculated using sine and cosine. The timing of high and low tide, the amplitude of the tides, the spring and neap cycles, all of these are described by trigonometric functions. The tides are the mathematics of the moon, the language of the ocean. The motion of the planets is a trigonometric phenomenon. The planets move in orbits that are close to circles. Their positions at any time can be calculated using sine and cosine. The relative positions of the planets, the timing of conjunctions and oppositions, the visibility of a planet in the night sky, all of these can be calculated using trigonometry. The solar system is a trigonometric system, a set of bodies moving in cyclic paths. The sine and cosine are not just tools for calculation, they are descriptions of the way the world works. They describe the motion of the Earth, the changing of the seasons, the rise and fall of the tides, the paths of the planets. They describe the structure of buildings, the forces in bridges, the stability of dams. They describe the sound of a voice, the color of a flower, the rhythm of a heartbeat. They are the mathematics of nature, the language of the universe. And they are here with you now, in the quiet of the room, in the stillness of the night. The sine and cosine are in the angle of your elbow, in the tilt of your head, in the curve of your spine against the mattress. They are in the light that falls across the ceiling, in the pattern of shadows, in the rhythm of your breathing. They have been here the whole time, quietly doing their work, and they will be here long after you have fallen asleep. The sine and cosine are not something you need to hold on to. They are something you can let go of, trust to be there, the way you trust the ground beneath you or the air around you. They are part of the fabric of things, part of the structure of the world. They are the mathematics of the quiet, the mathematics of the dark, the mathematics of the long, slow cycle of the night. If you find yourself drifting, let the image of the Earth carrying you through space fill your mind. You are lying still, but you are moving at thousands of miles per hour, carried along by the rotation of the Earth and its orbit around the Sun. The angles that describe that motion are the same angles that describe your elbow and your spine and the light on the ceiling. You are part of the same system, governed by the same relationships. The sine and cosine are the mathematics of your motion, the language of your journey through the dark. The story of trigonometry is not just a story about mathematics. It is a story about human curiosity and human need. It is a story about people looking at the world and asking questions. How far is that mountain? When will the flood come? Where will the star be tomorrow night? These questions were not abstract, they were practical. They mattered for survival, for agriculture, for navigation, for understanding the world and one's place in it. The rope stretchers on the Nile were asking a question about property. They needed to know where one field ended and another began. They found a way to answer that question using a knotted rope and a simple geometric fact. They did not know why the 3, 4, 5 triangle worked. They only knew that it did. but their practical need led them to a discovery that would eventually become part of a much larger system of knowledge. The Babylonian scribes were asking a question about patterns. They had observed that certain sets of numbers seemed to fit together in a regular way. They began to explore those patterns systematically, recording their findings on clay tablets. They did not know that they were laying the groundwork for a branch of mathematics. They were just curious. They wanted to understand the structure of the numbers they were working with. The Greek astronomers were asking a question about the sky. They wanted to predict the motions of the stars and planets. They needed a way to convert angles into distances, to turn what they could see into what they could calculate. Hipparchus built a table of chords to answer that need. Ptolemy used that table to build a model of the universe. Their model was wrong, but their mathematics was sound. They had found a tool that worked, even if their understanding of the cosmos was incomplete. The Indian mathematicians were asking a question about efficiency. They took the chord and halved it, making the mathematics simpler and more elegant. They gave the half-chord a name, and that name traveled across languages and cultures, becoming sine. They did not know that their small change would reshape the entire subject. They were just trying to make their calculations easier. The Islamic scholars were asking a question about completeness. They took the sine and extended it, adding tangent and the other functions. They developed spherical trigonometry, which was essential for navigation and for determining the direction of prayer. They treated trigonometry as a subject in its own right, separate from astronomy. They were building a body of knowledge that could be used for many purposes, not just one. The European mathematicians were asking a question about abstraction. They took the sine and cosine and treated them as functions, as rules that could be manipulated algebraically. They freed trigonometry from its geometric roots, turning it into a branch of pure mathematics. Viète and Euler and Fourier saw that the sine and cosine were not just tools for measuring triangles. They were descriptions of a deeper pattern, a pattern that appeared in waves and cycles and oscillations of all kinds. Each of these steps was driven by a need or a curiosity, each step built on the previous ones. The rope stretchers did not know about sine and cosine. The Babylonian scribes did not know about functions. The Greek astronomers did not know about Fourier analysis. But each of them contributed to the long chain of discovery that led to the trigonometry we have today. This is how knowledge grows, not in a straight line, not all at once, but slowly, piece by piece, across generations and cultures. Each generation asks its own questions and finds its own answers. Those answers become the foundation for the next generation. The sine and cosine that you might have learned in school are the product of this long process. They carry within them the accumulated wisdom of thousands of years. The sine and cosine are not just mathematical symbols. They are a record of human effort, a testament to the persistence of human inquiry. They are a reminder that the questions we ask matter, and that the answers we find can have consequences far beyond what we can imagine. The rope stretchers could not have imagined that their knotted ropes would lead to the Fourier transform. The Babylonian scribes could not have imagined that their clay tablets would be read by computers. The Greek astronomers could not have imagined that their tables of chords would be used to navigate satellites. But that is how knowledge works. It accumulates, it builds on itself, it spreads across cultures and across time. The sine and cosine are part of that accumulation. They are a link in a chain that stretches from the banks of the Nile to the satellites in orbit, from the clay tablets of Babylon to the digital signals in your phone, from the tables of Hipparchus to the Fourier transforms that compress your music. And the sine and cosine are still growing. They are still being used in new ways. They are still being extended and refined. Mathematicians are still discovering new properties of the sine and cosine, new identities, new connections to other areas of mathematics. Engineers are still finding new applications for them, new ways to use them to solve problems. The sine and cosine are not static. They are living ideas. The sine and cosine are also a reminder of the unity of knowledge. The same mathematics that describes the motion of the planets also describes the vibration of a guitar string. The same sine and cosine that are used to navigate a ship are used to process an image. The same relationships that the rope stretchers use to lay out a field are used to design a bridge. The unity is not accidental. It is a reflection of the underlying structure of the world. The world is not divided into separate subjects. Physics and mathematics and engineering and astronomy are not separate realms. They are all part of the same effort to understand the world. The sine and cosine are a thread that runs through all of them. They are a common language, a shared tool, a point of connection. This is one of the quiet lessons of trigonometry. The world is connected. The angles in your elbow are connected to the angles of the stars. The light on your ceiling is connected to the waves in the ocean. The rhythm of your breathing is connected to the orbit of the earth. The same mathematics describes all of it. The same sine and cosine that we have been walking through tonight are present in all of these things. And this connection is not something you need to hold on to. It is something you can let settle into the background, the way the warmth of a room settles into the air. It is something you can trust to be there, the way you trust the ground beneath you. It is part of the fabric of things, part of the structure of the world. The sine and cosine are not just ideas. They are descriptions of reality. They are the language of angles and waves, of cycles and oscillations, of motion and change. They are the mathematics of the world, and they are here with you now, in the quiet of the room, in the stillness of the night. There is a quiet corner of trigonometry that does not get as much attention as sine and cosine, but it is worth spending some time with, because it shows how the same ideas keep appearing in different forms. The tangent is the third of the main trigonometric functions, and it has its own story to tell. The tangent is the ratio of the opposite side to the adjacent side in a right triangle. It is the sine divided by the cosine. In the latter picture, the tangent of the angle at the ground is the height reached divided by the distance from the base of the ladder to the wall. It tells you the slope of the ladder. A steep ladder has a large tangent. A shallow ladder has a small tangent. The tangent is a measure of steepness. The tangent behaves differently from the sine and cosine. The sine and cosine are confined to values between -1 and +1. They are ratios of sides in a right triangle, and the hypotenuse is always the longest side, so the opposite and adjacent sides are never longer than the hypotenuse. The sine and cosine are always fractions of the hypotenuse, never larger than the hypotenuse itself. But the tangent is the ratio of the opposite side to the adjacent side, and the adjacent side can be very small. If the angle is close to 90 degrees, the adjacent side is close to 0, and the tangent grows very large. There is no upper bound on the tangent. It can be any positive number, and it can even become infinite, in a sense, when the angle reaches 90 degrees and the adjacent side disappears entirely. This behavior of the tangent, its tendency to grow without limit, makes it useful for describing situations where a line becomes nearly vertical. The slope of a line is its tangent. A line with a slope of 1 rises at 45 degrees. A line with a slope of 2 rises more steeply. A line with a slope of 10 is nearly vertical, and a line with an infinite slope is perfectly vertical, rising straight up with no horizontal run at all. The tangent gives us a way to talk about steepness in a single number, a number that covers the entire range from flat to vertical. The tangent also has a geometric interpretation on the unit circle. If you draw a line tangent to the circle at the far right point, and you extend the radius through the moving point until it intersects that tangent line, the length of the segment from the tangent point to the intersection is the tangent of the angle. This is a less direct interpretation than the sine and cosine, but it is consistent with the ratio definition. The tangent grows without bound as the angle approaches 90 degrees, because the radius line becomes parallel to the tangent line and never intersects it. The tangent is one of the original trigonometric functions. It was used by the Islamic scholars, who recognized its value for certain types of calculations. Al-Battani, the astronomer who refined the sine, also worked with the tangent, using it in his astronomical calculations. He found that the tangent was often more convenient than the sine for problems involving the height of celestial bodies above the horizon. The tangent of an angle is the ratio of the vertical to the horizontal, and in many practical situations, that is exactly the ratio you need. The tangent is also used in calculus. The derivative of the tangent is the secant squared, and the integral of the tangent is the natural logarithm of the secant. These relationships are part of the larger structure of calculus, the same structure that connects the sine and cosine to the exponential function. The tangent is not an isolated function. It is part of a family of functions, all connected by the same relationships. The tangent is also used in geometry. It appears in the law of tangents, which is a relationship between the sides and angles of a triangle. The law of tangents is less well known than the law of sines and the law of cosines, but it is a useful tool in certain situations. It says that the ratio of the difference of two sides to their sum is equal to the ratio of the tangent of half the difference of the opposite angles to the tangent of half their sum. This is a more specialized result, but it shows that the tangent has its own place in the geometry of triangles. The tangent also appears in the study of periodic functions. The tangent is periodic, but its period is pi, not 2 pi. This means that the tangent repeats its values every 180 degrees, rather than every 360 degrees. This is because the tangent is the ratio of sine to cosine, and both sine and cosine change sign at certain points, so the ratio repeats more often. The tangent has vertical asymptotes at odd multiples of 90 degrees, where the cosine is 0 and the tangent is undefined. The tangent is not as commonly used as the sine and cosine, but it is still an important part of trigonometry. It appears in many contexts, from geometry to calculus to physics. It is the function that describes slope, and slope is a fundamental concept in mathematics and science. The tangent is the mathematics of steepness, the language of incline. There are other trigonometric functions as well, though they are less commonly used. The secant is the reciprocal of the cosine. The cosecant is the reciprocal of the sine. The cotangent is the reciprocal of the tangent. These functions appear in some contexts, particularly in calculus and in certain types of integrals. They are part of the same family as the sine, cosine, and tangent, and they are connected by the same relationships. The secant has a geometric interpretation on the unit circle. It is the length of the line from the center to the tangent line, the hypotenuse of the right triangle formed by the radius, the tangent, and the secant. The cosecant has a similar interpretation, but with the roles of sine and cosine reversed. The cotangent is the reciprocal of the tangent, and it has a similar geometric interpretation. These functions are not as commonly used as sine and cosine, but they are still part of the subject. They appear in certain types of problems, and they are part of the larger structure of trigonometry. They are connected to the sine and cosine by simple reciprocal relationships, and they share many of the same properties. The sine, cosine, tangent, secant, cosecant, and cotangent are the 6 trigonometric functions. They are all defined in terms of the angles of a right triangle, or in terms of the unit circle. They are all connected by a web of relationships, identities that relate one function to another. They are the building blocks of trigonometry, the tools that we use to describe angles and distances. The relationships between the trigonometric functions are not arbitrary. They follow from the geometry of the right triangle and the unit circle. The identity that sine squared plus cosine squared equals 1 is a direct consequence of the Pythagorean theorem. The identity that tangent equals sine divided by cosine is a direct consequence of the definitions. The other identities follow from these basic relationships. The trigonometric functions are not just mathematical objects. They are descriptions of the way the world works. They describe the motion of the planets, the vibration of atoms, the propagation of light. They describe the sound of a voice, the color of a flower, the rhythm of a heartbeat. They are the mathematics of nature, the language of the universe. And they are here with you now, in the quiet of the room, in the stillness of the night. The sine, cosine, tangent, and the others are in the angle of your elbow, in the tilt of your head, in the curve of your spine against the mattress. They are in the light that falls across the ceiling, in the pattern of shadows, in the rhythm of your breathing. They have been here the whole time, quietly doing their work, and they will be here long after you have fallen asleep. The trigonometric functions are not something you need to hold on to. They are something you can let go of, trust to be there, the way you trust the ground beneath you or the air around you. They are part of the fabric of things, part of the structure of the world. They are the mathematics of the quiet, the mathematics of the dark, the mathematics of the long, slow cycle of the night. If you find yourself drifting, let the image of the unit circle carry you. Picture the point moving around the edge of the circle, its sine and cosine changing as it goes. Picture the tangent as the slope of the line, growing and shrinking, reaching toward infinity as the point approaches the top of the circle. These are the functions of trigonometry, the tools that we have been walking through tonight. They are old and useful, and they are still here, waiting for you, whenever you want to come back to them. The story of trigonometry is not complete without mentioning the strange and beautiful connection between sine and cosine and the world of complex numbers. This is a connection that seems, at first, to belong to a different branch of mathematics entirely, but it turns out to be one of the most important and far-reaching insights in the history of the subject. Complex numbers are numbers that have two parts. There is a real part, which is an ordinary number, and an imaginary part, which is a multiple of the square root of -1. The square root of -1 does not exist among ordinary numbers, because no ordinary number multiplied by itself gives a negative result. But mathematicians found that if you simply define a new number, often denoted by the letter I, to have the property that I squared equals -1, then a whole new world of mathematics opens up. Complex numbers are written as a plus b times I, where a and b are ordinary numbers. Complex numbers can be represented geometrically as points on a plane. The real part is the horizontal coordinate, and the imaginary part is the vertical coordinate. This is the same plane that we used for the unit circle. In fact, the unit circle is a circle in the complex plane, centered at the origin with radius 1. The points on the unit circle are exactly the complex numbers whose distance from the origin is 1. Here is where the connection to trigonometry appears. A point on the unit circle can be described by an angle, the angle that the radius makes with the positive real axis. The coordinates of that point are the cosine of the angle for the real part and the sine of the angle for the imaginary part. So a point on the unit circle can be written as cosine of the angle plus I times sine of the angle. This is a complex number with modulus 1. Now there is a remarkable result, due to Euler, that connects this complex number to the exponential function. The exponential function is usually defined for ordinary numbers. It is the function that describes growth, the steady increase of a quantity at a rate proportional to its current value. But Euler showed that the exponential function can be extended to complex numbers, and when you do that, something beautiful happens. The exponential of I times an angle is equal to cosine of the angle plus I times sine of the angle. This is Euler's formula. It is one of the most important formulas in all of mathematics. It connects the exponential function, which describes growth, to the sine and cosine, which describes circular motion. It shows that these two apparently different concepts are actually the same thing, viewed from different perspectives. Exponential growth, when extended to the complex numbers, becomes circular motion. Euler's formula has many consequences. One of the most famous is that when the angle is pi, the formula gives e to the power of I times pi equals -1. This is often written as e to the I pi plus 1 equals 0. This equation is sometimes called the most beautiful equation in mathematics because it relates 5 of the most fundamental constants in the subject: e, I, pi, 1, and 0. They are all connected by this single elegant formula. Euler's formula also gives a simple way to work with trigonometric functions. Instead of writing sine and cosine separately, You can write them as the real and imaginary parts of a complex exponential. This simplifies many calculations, especially in physics and engineering. The complex exponential is easier to manipulate than sine and cosine because it obeys the laws of exponents. Multiplication of complex exponentials corresponds to addition of angles, which is much simpler than the angle addition formulas for sine and cosine. This is why complex numbers are so useful in electrical engineering. Alternating current circuits are described by sine and cosine functions. The voltage and current in an AC circuit oscillate sinusoidally. By representing these oscillations as complex exponentials, engineers can analyze circuits using algebra instead of trigonometry. The complex representation turns differential equations into algebraic equations, which are much easier to solve. The same idea applies to quantum mechanics. The wave function that describes a particle is a complex function. It oscillates in time and space, and its behavior is governed by sine and cosine. The complex representation is natural for quantum mechanics because it allows the wave function to have both amplitude and phase. The amplitude is the modulus of the complex number, and the phase is the argument. The sine and cosine are the components of the wave function. The complex representation also appears in signal processing. The Fourier transform is often written using complex exponentials instead of sine and cosine. This simplifies the notation and makes the underlying structure clearer. The Fourier transform decomposes a signal into complex exponentials, which are the same as sine and cosine, but combined in a way that preserves both amplitude and phase information. The connection between sine and cosine and the exponential function is one of the great unifying insights of mathematics. It shows that the world of growth and the world of cycles are not separate. They are two aspects of the same underlying structure. The sine and cosine are the shadows of exponential growth in the complex plane. They are the real and imaginary parts of a complex exponential. This connection also gives a new way to think about the periodicity of sine and cosine. The exponential function is periodic when its argument is imaginary. The period is 2 pi times I. This means that e to the I theta repeats every 2 pi radians. The sine and cosine inherit this periodicity. They repeat every 2 pi radians because they are the real and imaginary parts of the exponential. The connection also gives a simple way to derive the angle addition formulas. The exponential of the sum of two angles is the product of the exponentials of the individual angles. This is a property of exponents. When you expand the product and equate real and imaginary parts, you get the angle addition formulas for sine and cosine. The complex exponential makes the derivation much simpler than the geometric proof. The connection also explains why the sine and cosine appear in so many different contexts. They are not just functions of angles, they are the components of a complex exponential, and the complex exponential is one of the most important functions in all of mathematics. It appears in differential equations, in linear systems, in probability theory, in number theory, and in many other fields. The sine and cosine go with it wherever it goes. The complex exponential is also the basis of the Fourier transform. The Fourier transform decomposes a signal into complex exponentials, which are the same as sine and cosine. This is why the Fourier transform is so useful. It represents a signal in terms of its frequency components, and those frequency components are complex exponentials. The sine and cosine are the real and imaginary parts of those exponentials. The complex exponential is also used in the study of waves. A wave can be represented as a complex exponential, with the real part being the physical wave. This is convenient because the complex exponential is easier to work with than sine and cosine. The derivative of a complex exponential is just a constant times the exponential, which is much simpler than the derivative of sine or cosine. The complex exponential is used in many areas of physics. It is used in optics, where light waves are represented as complex exponentials. It is used in acoustics, where sound waves are represented as complex exponentials. It is used in electromagnetism, where electromagnetic waves are represented as complex exponentials. It is one of the most widely used functions in all of physics. The connection between sine and cosine and the complex exponential is a testament to the unity of mathematics. It shows that different areas of mathematics are not isolated, they are connected by deep relationships. The sine and cosine are not just part of geometry, they are part of analysis, part of complex analysis, part of differential equations, part of signal processing. They are everywhere. And they are here with you now, in the quiet of the room, in the stillness of the night. The sine and cosine are in the angle of your elbow, in the tilt of your head, in the curve of your spine against the mattress. They are in the light that falls across the ceiling, in the pattern of shadows, in the rhythm of your breathing. They have been here the whole time, quietly doing their work, and they will be here long after you have fallen asleep. The sine and cosine are not something you need to hold on to. They are something you can let go of, trust to be there, the way you trust the ground beneath you or the air around you. They are part of the fabric of things, part of the structure of the world. They are the mathematics of the quiet, the mathematics of the dark, the mathematics of the long, slow cycle of the night. If you find yourself drifting, let the image of the complex plane carry you. Picture the unit circle, the points on its edge, the sine and cosine as coordinates. Picture the exponential function, the steady growth that becomes circular motion when extended to the complex plane. These are the same things, seen from different angles. The sine and cosine are the shadows of the exponential, and they are here with you now, in the quiet of the room, in the stillness of the night. There is a kind of quiet magic in the way that a single idea can take so many different forms. The sine and cosine began as measurements of triangles, as ratios of sides that rope stretchers used to lay out fields. They became tools for tracking the stars, tables of chords that astronomers used to predict the movements of the heavens. They became half-chords in India, abstract functions in Europe, coordinates on a unit circle, waves that describe sound and light and the rhythms of the natural world. And they became part of a larger mathematical structure, connected to exponential growth and complex numbers and the Fourier transform. But the sine and cosine are not just tools for calculation, they are also a way of thinking. They are a way of seeing the world as composed of cycles, of patterns that repeat, of motions that oscillate. They are a way of understanding that the world is not static, that it is always changing, always moving, always in flux. The sine and cosine give us a language for describing that change, a way of talking about the rhythms of nature. The world is full of cycles, the day and the night, the phases of the moon, the seasons of the year, the beating of a heart, the breathing of lungs, the ebb and flow of the tides, the rise and fall of prices in a market, the growth and decay of populations. All of these are cycles, patterns that repeat over time. Some cycles are regular, like the swing of a pendulum. Others are irregular, like the weather, but all of them can be described, at least in part, using the language of sine and cosine. The sine and cosine give us a way to measure the properties of cycles. The frequency of a cycle is how often it repeats. The amplitude is how large the oscillation is. The phase is where in the cycle you start measuring. These properties are the same whether you are talking about a sound wave, a light wave, a tide, or a heartbeat. The sine and cosine provide a common language for describing all of these different phenomena. This is one of the great insights of trigonometry. The same mathematics that describes the motion of a pendulum also describes the propagation of sound. The same sine wave that represents a musical tone also represents a radio signal. The same cosine that gives the height of a tide also gives the brightness of a star. The unity is not accidental. It is a reflection of the underlying structure of the world. The sine and cosine are not just descriptive, they are also predictive. If you know the properties of a cycle, you can predict its future behavior. You can predict when the tide will be high. You can predict where a planet will be on a given night. You can predict the frequency of a note that a guitar string will produce. The sine and cosine give us a way to look into the future, at least for cyclic phenomena. This predictive power is one of the reasons that trigonometry has been so useful throughout history. The ancient astronomers used trigonometry to predict the positions of the stars and planets. The early navigators used it to predict their position at sea. The modern engineers use it to predict the behavior of circuits and structures. The sine and cosine are tools for anticipation, for looking ahead. The sine and cosine are also tools for understanding the past. If you have a record of a cycle, you can analyze it to find its frequency and amplitude. You can determine what caused it. You can see how it has changed over time. The Fourier transform, which is built on the sine and cosine, is a tool for analyzing historical data, for finding patterns in the past that can inform the future. The sine and cosine are not just mathematical objects, they are part of the fabric of human experience. We experience cycles in our own bodies, in our own lives, in the world around us. The rhythm of our breathing, the beating of our hearts, the alternation of wakefulness and sleep, all of these are cycles. The sine and cosine are the mathematics of these experiences, the language of the rhythms of life. The sine and cosine are also part of the fabric of human culture. They appear in music, in art, in architecture, in literature. The rhythms of music are based on cycles. The proportions of buildings are based on geometric relationships. The patterns of poetry are based on repetition. The sine and cosine are not just in the mathematics textbooks, they are in the world around us, in the things we make and the things we do. The sine and cosine are a bridge between the abstract and the concrete. They connect the world of pure mathematics to the world of physical experience. They are a way of translating between the language of numbers and the language of the senses. They are a way of making the invisible visible, of bringing the hidden patterns of the world into view. And they are here with you now, in the quiet of the room, in the stillness of the night. The sine and cosine are in the angle of your elbow, in the tilt of your head, in the curve of your spine against the mattress. They are in the light that falls across the ceiling, in the pattern of shadows, in the rhythm of your breathing. They have been here the whole time, quietly doing their work, and they will be here long after you have fallen asleep. The sine and cosine are not something you need to hold on to. They are something you can let go of. Trust to be there, the way you trust the ground beneath you or the air around you. They are part of the fabric of things, part of the structure of the world. They are the mathematics of the quiet, the mathematics of the dark, the mathematics of the long, slow cycle of the night. If you find yourself drifting, let the image of a cycle carry you. Picture a pendulum swinging back and forth, its motion a smooth arc. Picture a wave rolling across the ocean, its crests and troughs following a regular pattern. Picture the moon going through its phases, the sun rising and setting, the seasons turning. All of these are cycles, and all of them are described by the same mathematics. The sine and cosine are the language of cycles, and they are here with you now, in the quiet of the room, in the stillness of the night. There is a kind of quiet wonder in the way that trigonometry, which began as a practical tool for measuring fields and tracking stars, has become so deeply embedded in the fabric of modern life. It is easy to go through a day without thinking about sine and cosine. They are not something you see or touch. They are not something you need to know to operate a phone or drive a car or listen to music. But they are there, underneath everything, quietly doing their work. Consider the simple act of taking a photograph. When you press the button on a camera, light enters through the lens and falls on a sensor. The sensor records the intensity of light at each point, creating an image. The image is then compressed and stored as a file. The compression algorithm, whether it is JPEG or some other format, relies on the Fourier transform, which is built on sine and cosine. The image is broken down into its spatial frequency components, and the less important components are discarded. This is why you can store thousands of photographs on a small device. The sine and cosine are doing the work. Consider the simple act of making a phone call. Your voice is converted into an electrical signal, which is then transmitted as a wave. The wave is modulated, sent through the air, and received by a tower. The tower sends the signal to another tower, and eventually to the phone of the person you are calling. The signal is demodulated and converted back into sound. All of this relies on trigonometry. The modulation and demodulation are trigonometric operations. The transmission and reception are based on wave behavior. The sine and cosine are the language of the communication. Consider the simple act of driving a car. The car's navigation system uses GPS, which relies on trigonometric calculations. The car's engine control system uses sensors that measure angles and positions. The car's stability control system uses algorithms that involve trigonometric functions. The car's entertainment system plays music that has been compressed using Fourier analysis. The sine and cosine are in the car, working quietly in the background. Consider the simple act of turning on a light. The electricity that powers the light is generated by a turbine, which is driven by steam, water, or wind. The turbine rotates, and its rotation is described by sine and cosine. The electricity that flows through the wires is alternating current, which oscillates sinusoidally. The light that comes from the bulb is a wave, with a frequency and amplitude described by sine and cosine. The sine and cosine are in the light. Consider the simple act of waking up in the morning. The sun rises, and its light falls on your face. The sun's position in the sky is described by sine and cosine. The length of the day, the height of the sun at noon, the timing of sunrise and sunset, all of these are calculated using trigonometry. The sine and cosine are in the morning light. Consider the simple act of breathing. Your lungs expand and contract in a rhythmic cycle. The cycle is not a perfect sine wave, but it is close. Your heart beats in a rhythmic cycle. The cycle is not a perfect sine wave, but it is close. The electrical signals that control your heart and lungs are waves, and they can be analyzed using Fourier techniques. The sine and cosine are in your body. Consider the simple act of sleeping. Your brain cycles through different stages of sleep, each with its own pattern of electrical activity. The patterns are analyzed using Fourier techniques, which are built on sine and cosine. The sine and cosine are in your dreams. Trigonometry is not just a subject in a textbook. It is a part of the world, a part of your life. It is in the things you use, the things you see, the things you do. It is in the light, the sound, the motion, the rhythm. It is in the world around you, and it is in you. The sine and cosine are not just mathematical functions. They are descriptions of reality. They are the language of cycles, the mathematics of waves, the foundation of so much of modern technology. They are the quiet workhorses of the modern world, the unsung heroes of the digital age. And yet, for all their importance, the sine and cosine are still the same functions that Hipparchus tabulated, that Aryabhata named, that Euler defined. They have not changed. They are still the same half-chords, the same ratios of sides, the same coordinates on the unit circle. They have been refined and extended, but they are still the same ideas. This is one of the quiet beauties of mathematics. The ideas do not age. They do not wear out. They do not become obsolete. The sine and cosine that were used to build the pyramids are the same sine and cosine that are used to build satellites. The sine and cosine that were used to navigate ships are the same sine and cosine that are used to navigate phones. The sine and cosine that were used to predict eclipses are the same sine and cosine that are used to compress images. The sine and cosine are timeless. They are as useful today as they were thousands of years ago. They are as relevant to the modern world as they were to the ancient world. They are a bridge across time, a connection between the past and the present, and they are a bridge across cultures. The sine and cosine were developed by people in Egypt, Babylon, Greece, India, the Islamic world, and Europe. Each culture contributed something, built on the work of the previous cultures, and passed the knowledge on. The sine and cosine are a product of human collaboration, a testament to the power of shared knowledge. The sine and cosine are also a bridge across disciplines. They are used in mathematics, physics, engineering, computer science, astronomy, geology, biology, medicine, finance, and many other fields. They are a common language, a shared tool, a point of connection between different areas of human endeavor. The sine and cosine are a reminder that the world is connected. The same mathematics that describes the motion of a pendulum also describes the propagation of light. The same sine wave that represents a musical note also represents a radio signal. The same cosine that gives the height of a tide also gives the brightness of a star. The unity is not accidental, it is a reflection of the underlying structure of the world. And the sine and cosine are a reminder that you are connected. The angle of your elbow, the tilt of your head, the curve of your spine, all of these are described by the same mathematics that describes the stars. You are part of the same system, governed by the same relationships. The sine and cosine are in you, as they are in the world around you. The sine and cosine are not something you need to hold on to. They are something you can let go of, trust to be there, the way you trust the ground beneath you or the air around you. They are part of the fabric of things, part of the structure of the world. They are the mathematics of the quiet, the mathematics of the dark, the mathematics of the long, slow cycle of the night. If you find yourself drifting, let the image of the connected world carry you. Picture the sine and cosine in the light, in the sound, in the motion. Picture them in the technology you use, in the world around you, in your own body. They are everywhere, quietly doing their work. And they have been here the whole time, and they will be here long after you have fallen asleep. And so we come to the end of this long, slow walk through an old and useful idea. It has been a journey that started with a knotted rope on the banks of the Nile, passed through clay tablets in Babylon, through the star charts of Greek astronomers, through the half-chords of Indian mathematicians, through the translations and extensions of Islamic scholars, through the algebraic reformulations of European mathematicians, and into the modern world of digital signals and satellite navigation. It has been a journey through thousands of years and across many cultures, a journey that has followed a single thread. The thread is the sine and cosine. They are the same functions that were used to measure fields and track stars. They are the same functions that were tabulated by Hipparchus, named by Aryabhata, defined by Euler. They have not changed. They are still the same relationships, the same ratios, the same coordinates on a circle. They have been refined and extended, but they are still the same ideas. The sine and cosine are a reminder that knowledge is cumulative. Each generation builds on the work of the previous generations. The rope stretchers did not know about sine and cosine, but they discovered the relationships that sine and cosine describe. The Babylonian scribes did not know about trigonometry, but they explored the patterns that trigonometry formalizes. The Greek astronomers did not know about Fourier analysis, but they built the tables that Fourier analysis would later use. Each generation added something, refined something, extended something. The sine and cosine are the product of this cumulative effort. The sine and cosine are also a reminder that knowledge is shared. The sine and cosine were not developed in one place by one culture. They were developed across many cultures, each contributing something, each building on the work of the others. The Egyptian rope stretchers, the Babylonian scribes, the Greek astronomers, the Indian mathematicians, the Islamic scholars, the European mathematicians, all of them contributed to the same body of knowledge. The sine and cosine are a product of human collaboration, a testament to the power of shared inquiry. The sine and cosine are also a reminder that knowledge is useful. The sine and cosine started as tools for measuring fields and tracking stars. They became tools for navigation, surveying, architecture, and engineering. They became the foundation of modern signal processing, communications, and imaging. They are used in physics, astronomy, geology, biology, medicine, finance, and many other fields. The sine and cosine are not just abstract ideas, they are practical tools, tools that have been used to solve real problems, to build real things, to improve real lives. The sine and cosine are also a reminder that knowledge is beautiful. There is a beauty in the way that the sine and cosine connect different areas of mathematics, different areas of science, different areas of human endeavor. There is a beauty in the way that they describe the cycles of the natural world, the rhythms of life, the patterns of the universe. There is a beauty in the way that they are both simple and profound, both ancient and modern, both practical and abstract. The sine and cosine are also a reminder that knowledge is never finished. There is always more to learn, more to understand, more to explore. The sine and cosine are still being studied, still being extended, still being applied in new ways. Mathematicians are still discovering new properties of the sine and cosine. Engineers are still finding new uses for them. The sine and cosine are not a closed subject. They are a living subject, still growing, still changing, still revealing new insights. The sine and cosine are also a reminder that knowledge is personal. The sine and cosine are not just things that exist in textbooks or calculators. They are things that you can understand, that you can feel, that you can carry with you. The sine and cosine are in the angle of your elbow, in the tilt of your head, in the curve of your spine against the mattress. They are in the light that falls across the ceiling, in the pattern of shadows, in the rhythm of your breathing. They are part of your experience, part of your world. The sine and cosine are not something you need to hold on to. They are something you can let go of. Trust to be there, the way you trust the ground beneath you or the air around you. They are part of the fabric of things, part of the structure of the world. They are the mathematics of the quiet, the mathematics of the dark, the mathematics of the long, slow cycle of the night. If you have drifted in and out along the way, that is fine. The ideas are still here, waiting for you, whenever you want to come back to them. There is no test, no deadline, no requirement to remember anything. The sine and cosine are patient. They have been here for thousands of years, and they will be here tomorrow night, and the night after that, and for as long as anyone cares to look. If you find yourself drifting now, let the image of the point on the circle carry you. Picture the point moving endlessly around the edge of the circle, its height tracing out sine, its horizontal position tracing out cosine. Picture the wave that the sine makes, rising and falling in a smooth, regular rhythm. Picture the cosine, the same wave, shifted slightly in time. Picture the tangent, the slope, growing without bound as the point approaches the top of the circle. Picture the complex exponential, the connection between growth and rotation, the unity of the sine and cosine with the rest of mathematics. Picture the rope stretchers on the Nile, pulling their knotted ropes through the mud. Picture the Babylonian scribes, pressing their wedge-shaped marks into wet clay. Picture the Greek astronomers, gazing up at the stars, building their tables of chords. Picture the Indian mathematicians, working with half-chords, giving them a name. Picture the Islamic scholars, translating and extending, treating trigonometry as a subject in its own right. Picture the European mathematicians, abstracting and generalizing, turning trigonometry into a branch of pure mathematics. Picture Euler, defining the sine and cosine on the unit circle, introducing the radian, connecting them to the exponential function. Picture Fourier, showing that any repeating pattern can be built from sine waves. And picture yourself, lying in the dark, surrounded by angles and cycles and waves. The sine and cosine are in the room with you. They are in the position of your body, in the light on the ceiling, in the sound of your breathing. They have been here the whole time, and they will be here long after you have fallen asleep. The sine and cosine are not just mathematical functions. They are descriptions of reality. They are the language of angles and waves, of cycles and oscillations, of motion and change. They are the mathematics of the world, and they are here with you now, in the quiet of the room, in the stillness of the night. Let that be the last thing tonight, not a fact to hold on to, just a feeling of things quietly fitting together, the way they have been the whole time you have been drifting, and the way they will keep on fitting together long after you have fallen the rest of the way asleep.